Hello there, and welcome to Physics with William, where curiosity gets cozy and science takes the scenic route to slumber. Tonight's gentle journey is about rockets. Those roaring towers of fire that lifted humanity off the ground, carried us beyond the clouds and gave us our first real footsteps on another world. Rockets are among the most dramatic machines we have ever built. They shake the earth before they leave it. They turn fuel into thunder. They rise on a pillar of flame as if the planet itself is trying just for a moment to light a candle tall enough to touch the stars. And yet, for all their beauty, power and courage, rockets may not be the true future of space travel. That sounds almost ungrateful, does it not? After all, rockets gave us spaceflight. Rockets carried satellites into orbit, sent probes to other planets, helped astronauts circle Earth, and brought human beings to the moon. If you have ever watched a launch, even on a screen, there is something difficult to ignore about it. The countdown becomes a kind of shared heartbeat. The engines ignite, the smoke spreads, the vehicle begins to move, slowly at first, almost reluctantly, and then the whole tower climbs upward with the confidence of something that should not be possible but somehow is. It is hard not to feel a little proud of our strange species in that moment. We are small creatures from a wet, rocky planet, and we built a machine that can push itself into the sky. But here is the quiet problem hiding behind all that flame. Rockets are not magic. They are bargains. They give us motion by spending mass. They move forward by throwing something backward. Most of what a rocket carries is not people, not cargo, not scientific instruments, not food, not water, not the delicate dreams of future explorers. Most of what it carries is fuel. Fuel to lift fuel. Fuel to lift the fuel that lifts more fuel. It is a brilliant idea, and at the same time, a rather exhausting one. Like packing for a weekend trip and discovering that your suitcase needs another suitcase, and that suitcase needs a small trailer, and the trailer somehow needs its own lunch. Before we go much further, I would love to know where in the world are you listening from tonight, and what time is it where you are? Are you tucked away under a quiet sky, somewhere the stars are already out? Or are you listening in the daytime while the world is still busy and the kettle, perhaps, is pretending to boil faster than it really is? It is a fitting question for a journey like this, because space travel is also a story about time, the time it takes to leave Earth, the months it takes to reach Mars, the years it takes for spacecraft to cross the outer solar system, the thousands of years that separate us, with today's technology, from even the nearest stars. Every dream of space travel eventually becomes a question of distance and time, and rockets, magnificent though they are, begin to look very limited when those distances become truly large. If you find this voyage soothing, intriguing, or simply a calm place to rest your mind for a while, I would be ever so grateful if you gave the video a like and maybe subscribed. It helps this little corner of science and sleep reach others who might enjoy drifting through the universe without needing to memorize a single equation. And I do hope tonight's subject does not keep you too awake. There is always a slight risk, of course, when discussing machines that explode deliberately in a very controlled direction. But we will keep our pace gentle, no alarms, no rush, just a slow walk through the firelight of human invention and the strange future waiting beyond it. So settle in, let your thoughts loosen a little, and let us begin with a simple image. Imagine standing near a launch site before dawn. The air is cool. The rocket stands in the distance, white and still, held upright by a tower of steel. It does not look fast yet. It does not look like a thing that belongs to motion. It looks more like a monument, a narrow building that someone has placed on the ground by mistake. Around it are pipes, tanks, cables, floodlights, vehicles, and people checking things, checking them again, and then checking the things that check the things. Spaceflight may look like drama from far away, but close up it is a great deal of careful plumbing. Inside that rocket is a simple principle, though the engineering behind it is anything but simple. Burn propellant, make hot gas, send that gas blasting out the back, and the rocket moves the other way. That is the heart of it. It is not pushing against the air, It works in space precisely because it carries its own reaction mass. A rocket is not climbing like a bird or floating like a balloon. It is throwing part of itself away with tremendous speed, and by doing that, the rest of it moves forward. There is something almost tragic about it. To travel, the rocket must lose itself. This is why rockets are so powerful at the beginning and so limited over long journeys. Chemical rockets are excellent at producing enormous thrust very quickly. They can lift heavy payloads off the surface of Earth, where gravity is strong and the atmosphere is thick. That is no small achievement. Earth is not an easy place to leave. Our planet holds on tightly. It wraps us in air, gravity, weather, and comfort. A rocket has to fight through all of that in the first few minutes, carrying everything it needs while burning through fuel at a rate that would make an ordinary engine look shy. In those first moments, chemical rockets are exactly what we need. Strong, fierce, impatient, willing to trade fuel for speed with almost ridiculous enthusiasm. But space is not just about leaving Earth. Leaving Earth is only the beginning. It is like rowing away from the shore and then realizing the ocean is much larger than the beach made it look. Once we are in space, a different problem appears. We no longer need the same kind of brute force. We need endurance. We need efficiency. We need ways to keep accelerating gently, slowly, patiently, without carrying mountains of fuel. A chemical rocket is like a sprinter. It is explosive, fast and spectacular, but it cannot sprint all the way to Mars and certainly not all the way to another star. For deep space, we may need machines that behave less like fireworks and more like quiet persistence. This is where the future begins to look strange. Not strange in a fantasy sense, though some ideas do lean comfortably against the edge of science fiction. Strange because the best way to travel far may not involve roaring engines at all. It may involve ion thrusters, which push spacecraft with tiny streams of electrically accelerated particles. These engines are so weak that if you stood beside one on Earth, it would not knock over a paper cup. And yet, in the emptiness of space, where there is no friction to slow you down, a small push that continues for months or years can become powerful in a different way. Not powerful like a thunderclap, powerful like a river wearing away stone. Then there are nuclear engines, a possibility that has lived in the minds of engineers for decades. Instead of relying only on chemical reactions, a nuclear rocket could use the heat from a reactor to send propellant out at far greater efficiency. That could shorten trips to Mars, reduce the time astronauts spend exposed to radiation and weightlessness, and make journeys through the inner solar system feel less like heroic endurance tests and more like practical transportation. Not easy, of course. Nothing about nuclear propulsion is easy. It comes with engineering challenges, political concerns, safety questions, and the general nervousness people feel when the words nuclear and rocket appear in the same sentence. Understandably so. There are solar sails too, which sound almost too gentle to be serious. A spacecraft spreads a vast, thin reflective sheet and lets sunlight push against it. Not wind, not air, but light itself. Photons have no rest mass, but they do carry momentum, and when they strike a sail, they can give it a tiny nudge. A very tiny nudge. The sort of nudge that would be useless for getting out of a parking space. But in space, patience is everything. Given enough time, sunlight can keep pushing, no fuel tank required, no exhaust plume. Just a sail catching the pressure of starlight. It is one of those ideas that sounds ancient and futuristic at once, like a ship crossing an ocean no sailor has ever seen. And then the ideas grow even more unusual: space tethers. Rotating cables that could exchange momentum with spacecraft, throwing them onward without burning fuel in the usual way. Laser propulsion, where a powerful beam from far away pushes a lightweight craft to enormous speeds. Electron beams, magnetic sails, fusion drives, antimatter dreams, and the famous warp drive, that strange mathematical temptation where space itself might be shaped, compressed, or expanded around a vehicle. Some of these concepts are grounded in real engineering studies. Some are distant. Some may never work. Some may turn out to be impossible for reasons we do not yet understand. But they all come from the same realization. If we want to travel far, truly far, we cannot simply build a bigger version of what we already have and expect the stars to come closer. This has happened before. Human beings often begin by copying what nature already does. We watched birds and dreamed of wings. Early flying machines flapped because birds flapped. It seemed obvious. If birds fly by flapping, then surely humans must flap too. But the future of flight was not a mechanical bird. It was fixed wings, propellers, jet engines, lift, pressure, and control surfaces. We did not conquer the sky by becoming birds. We conquered it by understanding the deeper principles that let birds fly, and then taking a different path. Rockets may be in a similar position. They got us into space. They were the first answer. But the next answer may not look like a taller rocket, or a louder rocket, or a rocket with a more heroic flame. It may look like something quieter, stranger, and at first less impressive to the eye. That is often how the future arrives. Not always with a roar. Sometimes it begins as a weak signal in a laboratory, a test article on a stand, a little engine glowing blue in a vacuum chamber, a sheet of material so thin it barely seems real, a cable spinning in orbit, a beam pointed across space. The first version of a future technology rarely looks like destiny. It usually looks awkward, fragile, expensive, and slightly unreasonable. The first airplanes were not sleek airliners. The first computers did not fit in pockets. The first rockets were not moon machines. They were experiments, weapons, fireworks, mathematical guesses wrapped in metal. Only later do we look back and say, of course, it was obvious. It was never obvious. For now, chemical rockets remain essential. That is important to say clearly. Rockets are not useless. They are not obsolete. They're not embarrassing old machines waiting to be retired like a bicycle with one squeaky wheel. They're extraordinary, and we will probably need them for a long time, especially for leaving Earth and landing on worlds with gravity. The future may not be rocketless. It may be rocket plus. Rockets for the first hard climb, electric engines for long cruising, nuclear propulsion for fast transfers, sails for patient journeys, beam propulsion for tiny craft headed toward nearby stars, different tools for different distances. The mistake is not using rockets. The mistake is imagining that rockets alone can carry every dream we have. Because the solar system is big in a way the human mind resists. Mars is close, astronomically speaking, but still far enough that a mission can take many months. Jupiter is much farther. Saturn farther still. The Kuiper belt waits in cold darkness beyond Neptune, and the nearest star system is so far away that our fastest spacecraft would need tens of thousands of years to reach it. At that scale, chemical rockets are not merely slow. They reveal the boundary of an era. They tell us that we have entered space, yes, but we have not yet learned how to move through it freely. We are like sailors who have pushed a canoe into the shallows and begun dreaming of crossing every ocean. There is something humbling about that. It reminds us that reaching orbit was not the end of the story. Landing on the moon was not the end either, even though it may have felt for a moment like the peak of all possible adventure. Each achievement simply revealed the next distance. The first airplane made the world smaller, but it also made the sky larger. The first rocket made the planet feel breakable, but it also showed us the scale of everything beyond it. Mars is not just a destination. It is a test of whether humans can learn to travel in a new way. Deep space is not just emptiness. It is a question. How patient are we? How clever can we be? How much are we willing to rethink? The answer may depend on whether we can let go of the romance of the flame, at least a little. Rockets are cinematic. They look like progress. They sound like progress. A solar sail, by comparison, may look almost still. An ion engine may whisper instead of thunder. A nuclear thermal rocket may not produce the same bright plume that fills a launch broadcast with drama. A laser-pushed probe may not carry astronauts at all, only a wafer, thin craft racing silently into the dark. But space does not care what looks impressive. Space rewards physics. It rewards efficiency, patience, and the ability to use the environment instead of fighting it constantly. The machines that carry us farthest may not be the loudest. They may be the ones that waste the least. This is the heart of tonight's journey. Rockets took us upward, but the future may require us to think sideways. To stop asking only how much fuel we can carry, and start asking how little fuel we can need. To stop imagining space travel as one huge blast, and start seeing it as a long conversation with gravity, sunlight, magnetism, nuclear energy, and motion itself. The next great leap may not be a single invention. It may be a whole family of strange methods, each suited to a different kind of journey. One for Mars, one for the asteroids, one for the outer planets, one perhaps for the first tiny messenger to another star. And as we move through these ideas, gently and slowly, it is worth keeping one comforting thought nearby. Every age has had a limit that seemed permanent. There was a time when human flight seemed impossible. Then it became dangerous, then experimental, then ordinary enough that people complained about legroom. There was a time when space itself seemed unreachable. Then a satellite crossed the sky. Then a human being looked down at Earth from orbit. Then footprints appeared in lunar dust. The impossible has a habit of becoming difficult, and then, with enough work, becoming something people schedule. So tonight, we're not saying goodbye to rockets. We are thanking them and then looking beyond them. We are standing beside the launch pad, watching the fire rise and asking what comes after the fire. What carries us when burning fuel too quickly is no longer enough? What moves a spacecraft when the destination is too distant for brute force? What kinds of engines belong not to the first few minutes of a journey, but to the long quiet years that follow? To answer that, we first need to understand why rockets work so beautifully, why they changed everything, and why the very thing that makes them powerful also makes them limited when the road ahead stretches far past the moon, past Mars, and into the deep dark waiting between worlds. To understand why rockets may not be enough for the future, we first have to appreciate why they're such astonishing machines in the present. It is easy to become impatient with rockets when we compare them with dreams of starships and distant worlds. We look at the huge towers of fuel, the enormous cost, the violent launch, the long travel times, and we are tempted to say there must be a better way. And yes, perhaps there must be. But before we move beyond rockets, we should give them their proper moment in the warm light of respect. Because rockets solve one of the hardest problems any machine can face. They work where there is nothing to push against. That is the first lovely trick. A car needs a road, a boat needs water, a plane needs air flowing over its wings. A rocket can leave all of that behind. It does not need ground beneath it, or wind around it, or an atmosphere to lean on. It carries its own little world of motion inside its tanks. Fuel and oxidizer, carefully stored, are brought together in a chamber where they burn with enormous intensity. That burning creates hot gas. The gas rushes out of the engine at very high speed, and because the gas is thrown backward, the rocket is pushed forward, simple in principle. Terrifyingly complicated in practice. A rocket engine is basically a controlled explosion that has been persuaded to behave itself for several minutes, which is a bit like asking a dragon to do accounting. This is why rockets became the key to space. Balloons could rise, but only through air. Airplanes could fly, but only inside an atmosphere. Cannons could throw objects upward, but not gently, and not with much concern for anyone sitting inside. Rockets, however, could carry their power with them. They could keep pushing even as the air thinned, even as the sky darkened, even as Earth became a curved blue shape below. Once people understood that a vehicle did not need to push against the air, but only needed to throw mass in one direction to move in the other, the door to space opened. Not easily, not politely, but it opened. There is something almost stubborn about a rocket launch. Earth says stay, gravity says stay, the atmosphere says stay. The rocket answers by burning through tons of propellant in a few minutes. It is not subtle, it is not relaxed, it does not negotiate. A launch vehicle has to lift itself, its payload, its engines, its structure, and all the fuel it has not yet burned. That last part is the troublemaker. At the start of launch, a rocket is heavy because it is full, but it needs that fullness in order to become light. So the rocket begins its journey at its worst possible moment, when it is carrying the greatest burden and has the farthest left to go. If you have ever tried to climb stairs while holding groceries, a suitcase, and one suspiciously heavy bag you do not remember packing, you have a very mild version of the idea. The beauty of chemical rockets is that they can produce tremendous thrust. Thrust is the push that gets a vehicle moving, and when it comes to lifting off from Earth, thrust is not optional. A spacecraft sitting on the launch pad is not in a gentle environment. It is deep inside a gravity well, under a thick atmosphere surrounded by pressure, drag, and the full authority of our planet. To rise, the rocket must produce more upward push than its own weight pulling downward. Not later, not gradually, immediately. This is where chemical rockets shine. They can release energy very quickly, turning stored propellant into a violent stream of exhaust, giving the vehicle the hard shove it needs to climb. That is why the most famous launches are so dramatic. The flame, the smoke, the shaking ground, the deep rolling sound that seems to enter the body rather than the ear. All of that is the price of overcoming gravity at the start. A rocket does not glide into space, it fights its way there. And in those first minutes, the fight is intense. The engines must run with extraordinary reliability under extreme heat and pressure. Pumps must move enormous amounts of liquid in a short time. Tanks must hold cryogenic fluids, sometimes kept so cold that the outside of the rocket frosts over in the humid air. Valves must open at the right time. Computers must guide the vehicle through a path that keeps it from tearing itself apart. Everything must happen correctly while the machine is vibrating, accelerating, and burning itself lighter by the second. A rocket launch is not just a climb upward. It is a careful sideways race. That may sound odd, because when we watch a launch, the rocket seems to go straight up at first. But reaching space is not the same as reaching orbit. You can go up and come back down. That is a very expensive jump. To stay in space around Earth, a vehicle has to move sideways fast enough that as it falls, the curve of Earth falls away beneath it. Orbit is falling without hitting the ground. A rocket must therefore gain altitude and sideways speed. It must climb out of the thickest air, then tilt and accelerate around the planet. This graceful turn is one of the hidden dances of launch. From the ground, it may look like a pillar of fire. In reality, it is a carefully timed path from sitting still on Earth to falling endlessly around Earth. This is where the fuel begins to vanish at a breathtaking pace. A rocket needs fuel to accelerate. But the fuel itself has weight. So at the start, much of the engine power is spent lifting fuel that will be burned later. Then more fuel is spent lifting the tanks that hold the fuel, the structure that supports the tanks, and the engines that burn the fuel. The larger the goal, the more propellant you need. But adding more propellant makes the vehicle heavier, which means you need still more propellant. There is a cruel little loop here, a loop so important that spaceflight has spent generations trying to outsmart it. It is not just that rockets use fuel. It is that rockets must carry the fuel they have not yet used, and that makes every extra bit of journey more expensive than intuition expects. This is the reason rockets are built in stages. A single giant rocket could carry fuel, burn it, and continue upward. But it would also have to carry the empty tanks and engines long after they stopped being useful. That would be like finishing a drink and then carrying the empty bottle in your hand for the rest of a marathon because you feel sentimental about it. Staging is the practical answer. When a section of the rocket has used its propellant, it is dropped away. The remaining vehicle becomes lighter, and the next stage takes over. This is both brilliant and slightly heartbreaking. A rocket reaches space by shedding pieces of itself. It climbs by leaving behind the parts that helped it climb. Staging made orbital flight possible. It made moon missions possible. It makes many modern launches possible. But staging also reveals the deep problem. The rocket is fighting against mass at every step. It needs structure strong enough to survive launch, but light enough not to waste fuel. It needs engines powerful enough to lift everything, but efficient enough to make the trip worthwhile. It needs tanks large enough to hold propellant, but not so heavy that they defeat their purpose. Rocket design is an art of ruthless compromise. Every bolt matters. Every kilogram matters. A small saving in mass can ripple through the whole vehicle. Because less mass means less fuel needed to lift that mass, which means smaller tanks, which means less structure, which means still less fuel. Space engineers are not obsessed with mass because they enjoy suffering over spreadsheets. They're obsessed with mass because mass is the quiet ruler of rocketry. And yet, for all this difficulty, chemical rockets work beautifully within their proper role. They are very good at getting things off planets. They are very good at short bursts of strong acceleration. They are very good at lifting payloads into orbit and sending spacecraft onto paths toward the Moon, Mars, and beyond. They are rugged in a strange way, not simple, but proven. They can be tested, improved, and launched again. Modern rockets have become more capable than ever, especially with reusable boosters that return to Earth instead of falling away forever. Reuse is a major step. It reduces cost, changes the economics of launch, and makes access to orbit feel less like throwing away a skyscraper every time you want to mail a telescope upward. But reusability does not erase the deeper limit. It helps with the first part of the journey, the climb from Earth to space. It does not magically make chemical propulsion ideal for crossing the solar system quickly, and it certainly does not make it suitable for interstellar travel. Once in space, a chemical engine can perform burns to change course, speed up, slow down, or enter orbit around another world. But every burn consumes propellant. Every planned maneuver must be paid for in mass, carried from the beginning, or picked up somehow along the way. There is no cosmic petrol station waiting politely between Earth and Mars, although if there were, one imagines the prices would be shocking. The reason chemical rockets run out so fast is not because engineers are wasteful. It is because chemical energy has limits. When fuel and oxidizer react, they release a certain amount of energy. That energy can heat exhaust and throw it backward, but there is only so much speed the exhaust can gain from ordinary chemical reactions. If you want more push for longer, you need more propellant. More propellant means more mass. More mass means more difficulty. The same principle that makes rockets possible also traps them. They must throw something away to move, and for long journeys they must throw away a great deal. This is not a problem when the mission is brief or when the goal is simply to reach orbit. The burn is intense, the fuel is spent, the vehicle arrives where it needs to be. But deep space asks for a different kind of travel. Imagine trying to cross an ocean in a boat that must carry all the wood it will burn for power, and also carry the wood needed to carry the wood, and also throw the burned wood into the sea as it goes. That is not a perfect comparison, but it captures the feeling. The farther you want to go, and the faster you want to get there, the more punishing the fuel problem becomes. Mars shows this clearly. Mars is not impossibly far by cosmic standards. It is our neighbour. A rusty, cold, dusty neighbour, but a neighbour all the same. And yet sending humans there is hard, partly because the journey is long. With current chemical-based mission designs, travel times are measured in months. During that time, astronauts would be exposed to space radiation, weightlessness, isolation, and all these psychological joys of living inside a metal container where every object floats away unless politely restrained. Shortening that trip would be valuable. It would reduce risk. It would make missions more flexible. But shortening the trip using chemical rockets alone quickly becomes expensive in propellant terms. Faster travel requires more energy. More energy means more propellant. More propellant means a bigger vehicle. and a bigger vehicle needs still more launching capacity just to begin. This is why future Mars missions often involve complicated plans, multiple launches, assembly in orbit, refueling, pre-positioned supplies, careful timing when Earth and Mars are favourably aligned. These are not signs that engineers lack imagination. They are signs that chemical rockets are being stretched close to the edge of what makes sense. The machines can do it, perhaps, but they do it with effort, cost, and many constraints. It's like asking a very strong horse to pull a train. You may admire the horse, you may even get the train to move a little, but eventually you start thinking about engines. Beyond Mars, the limits become even clearer. Robotic probes have reached the outer planets using chemical launchers combined with clever gravity assists. A gravity assist is one of the great tricks of spaceflight. A spacecraft flies close to a planet and uses the planet's motion to change its own path and speed. It is a kind of celestial slingshot, though not quite in the playground sense. This method has sent spacecraft on grand tours of the outer solar system, allowing small machines to visit worlds that would otherwise require far more fuel. But gravity assists depend on timing. They depend on the positions of planets. They are elegant, but they are not a universal engine. They are more like borrowing momentum from the solar system when the arrangement is kind enough to lend it. For human travel, waiting years for the perfect alignment is not always ideal. For cargo, perhaps patience is acceptable. For astronauts, speed matters more. The longer people spend in deep space, the more food, water, shielding, medical support and life support they need. And of course, carrying more supplies adds more mass, which adds more launch requirements. Again, the loop appears. Fuel and mass and fuel. The rocket is not failing. It is simply obeying physics. And physics is not known for making exceptions because humans are enthusiastic. The nearest stars make chemical rockets look almost comically limited. Even the fastest human-made spacecraft would take many thousands of years to reach another star system. A chemical rocket cannot carry enough fuel to push a large spacecraft anywhere near the speeds needed for interstellar journeys within a human lifetime. The numbers become so large that they stop feeling like engineering and start feeling like a bedtime story told by a calculator with no mercy. If the goal is another star, ordinary rockets are not just slow, they are the wrong tool. That does not make them primitive. A ladder is not primitive because it cannot cross an ocean. It is simply meant for a different task. The future of space travel may therefore begin with a more careful understanding of what rockets are truly for. They are launch tools, they are departure tools, they are sometimes landing tools, they are excellent at delivering force quickly. They are the opening move in the game of space, but they are not necessarily the whole game. Once a spacecraft is already in space, far from Earth's surface, the need for high thrust becomes less urgent. There is no road friction, no air resistance, no constant need to keep an engine running just to maintain speed. A spacecraft can coast for months or years. In that environment, a gentler engine that runs for a very long time can outperform a powerful engine that burns out quickly. This is the important shift. Space rewards endurance in a way Earth often does not. Think of two travellers crossing a frozen lake. One sprints with great power, but tires quickly. The other takes tiny steps and never stops. At first, the sprinter looks impressive. For short distances, the sprinter wins easily. But if the lake is wide enough, the steady traveller begins to matter. In space, where there is almost nothing to slow you down, a tiny continuous push can build up over time. That is why electric propulsion becomes so interesting. It produces very little thrust, sometimes less than the weight of a piece of paper on Earth, but it can keep going for a long time using far less propellant. It is not useful for launching from Earth. It would be like trying to lift a house with a polite suggestion, but in space, polite suggestions can add up. This contrast is at the centre of the story. Chemical rockets are beautiful because they are strong. They run out fast because strength comes at the cost of appetite. They burn propellant quickly to create the thrust needed for the hardest parts of flight. Electric engines, solar sails, nuclear systems, and other future concepts all try, in different ways, to escape that appetite. Some use energy more efficiently, some use fuel differently, some try to avoid carrying fuel at all. Each is an answer to the same old problem. How do you move through space without spending most of your journey carrying the thing you plan to throw away? There is also a psychological reason rockets still dominate our imagination. They're easy to understand emotionally. Fire means power. Noise means power. A launch looks like action. A faint blue ion glow or a thin sail pushed by sunlight does not feel powerful in the same way. It feels delicate, almost suspiciously calm. But the universe is not impressed by noise. The universe does not applaud a louder engine. It simply follows motion, energy, mass, and time. A quiet engine that works for years may be more useful than a spectacular engine that finishes its work in minutes. So when we say rockets are not the future of space travel, we do not mean that they are going away. We mean that the future cannot be built from launch flames alone. The rocket will still be there at the beginning, lifting us from the ground, breaking through the lower sky, giving humanity that first fierce shove into orbit. But after that, beyond the roar, another kind of travel must take over. A slower, stranger, more patient kind. And to see why, we need to look more closely at the fuel problem itself, the hidden arithmetic of mass that shapes every mission, every spacecraft, and every dream of going farther than rockets can easily take us. The fuel problem in space travel is easy to underestimate because on Earth, we're used to machines that can refuel, breathe air, roll on roads, or float in water. A car does not carry the road with it. A ship does not carry the ocean. An airplane does not carry all the air it needs for lift and combustion, which is quite convenient, because passengers already complain enough about luggage fees. But a rocket is different. A rocket has to carry almost everything that makes its motion possible. It carries the fuel, the oxidizer that lets the fuel burn, the tanks, the engines, the pipes, the pumps, the guidance systems, the structure, the payload, and often more fuel just to lift all the fuel it has not yet used. This is where space travel begins to feel less like adventure, and more like a very strict packing problem. At first, it sounds simple. If you want to go farther, take more fuel. If you want to go faster, take more fuel. If you want to slow down at the destination, take more fuel. It is the sort of answer that feels sensible for about 3 seconds. Then the trouble arrives. More fuel makes the spacecraft heavier. A heavier spacecraft needs even more fuel to move. That extra fuel also has weight, so now you need more fuel to move the extra fuel. And that added fuel also needs tanks, structure, and support. The problem grows on itself. It is like trying to save money by buying a larger wallet, then needing a larger bag for the wallet, then needing a larger car for the bag, and before long you have started a small logistics company by accident. This is sometimes called the tyranny of the rocket equation, although we do not need the equation itself tonight. The idea is enough. Rockets do not scale gently. Small changes in what you want at the end can demand huge changes at the beginning. If you want a little more speed, or a little more payload, or a little more flexibility, the required starting mass can grow very quickly. This is why rockets are often mostly propellant, not partly, mostly. A launch vehicle sitting on the pad may look like a spacecraft, but in a very real sense it is a giant flying fuel tank with an important object at the top. The useful payload may be a surprisingly small fraction of the whole. The rest is the price of getting that payload moving fast enough, high enough, and in the right direction. This can feel almost unfair. After all, a rocket looks so powerful. It roars, it shakes, it pushes upward with astonishing force. Surely something that dramatic should be able to carry whatever we ask of it. But spaceflight is not impressed by drama. Gravity asks for payment in energy, speed asks for payment in propellant. Every kilogram added to a mission must be justified. A chair has a cost, a window has a cost, A thicker wall has a cost. A spare part has a cost. A snack has a cost. Even the packet the snack comes in has a cost, which is probably why space food never seems to arrive in a large decorative tin with a ribbon on it. The universe is not cruel exactly, but it is very careful with mass. The first great weight problem is leaving Earth. Earth is a wonderful home, but a difficult starting point. It is large enough to hold a thick atmosphere and strong enough to make escape hard. To reach orbit, a rocket must not only climb upward, it must also build enormous sideways speed. It must fight gravity while pushing through air, all while carrying the propellant it has not burned yet. This is why the first stage of a rocket is usually so huge. Its job is not elegant deep space travel. Its job is brute effort. It must get the whole stack moving and rising, taking the worst part of the burden while the vehicle is still heavy and low in the atmosphere. Then comes the strange logic of throwing away the machine as you go. Staging may seem wasteful at first, especially if you imagine building a car that drops its rear half on the motorway once the fuel tank is empty. But for rockets, shedding dead weight is essential. Once a stage has burned its propellant, the tanks and engines attached to that stage become a burden. Keeping them would mean wasting fuel to accelerate empty hardware, so the rocket lets them go. A booster falls away. A stage separates. The remaining vehicle continues lighter than before. It is a practical solution, but also a reminder that rockets survive the tyranny of fuel partly by discarding parts of themselves. They do not carry everything to the end. They cannot afford to. This is one reason reusable rockets are so important. If a booster can return and fly again, it changes the economics of launch. It means that not every mission has to throw away such expensive hardware. It makes reaching orbit more routine and more affordable. That is a tremendous achievement, and one worth admiring. But even reuse does not remove the fuel problem. It does not change the fact that chemical rockets need propellant, and lots of it, to create the speed needed for orbit. It does not make deep space suddenly easy. Reuse helps with cost and access. It does not make chemical energy limitless. A reusable booster is still a rocket, and a rocket still has to obey the deep bargain of throwing mass backward to move forward. Once a spacecraft reaches orbit, the situation changes, but the weight problem does not disappear. In orbit, you're no longer fighting the atmosphere. You do not need continuous thrust to keep moving. That is one of the beautiful things about space. Give a spacecraft the right motion, and it will coast silently, faithfully, for a very long time. But coasting is not the same as choosing freely. To go to the Moon, Mars, or the outer planets, you have to change your path. To enter orbit at your destination, you often have to slow down. To land, you may need more propulsion. To return home, you need still more. Every planned change has to be paid for. The bill may come at launch, in the form of propellant you carried from Earth, or it may come later through refueling, gravity assists, or clever mission design. But the bill always exists. Mars is a good example because it sits in that awkward place between near and far. It is close enough that we can imagine sending people there, and far enough that the fuel problem becomes serious. A crewed Mars mission is not just a spacecraft with astronauts sitting politely in seats until arrival. It needs life support, radiation shielding, food, water, tools, spare parts, habitats, landing systems, return systems, and enough safety margin to handle things that do not go according to plan. And in space, something not going according to plan can be a little more serious than forgetting your umbrella. All of that mass must either be launched from Earth or produced somewhere else, perhaps in orbit, on the Moon, or eventually on Mars itself. Until then, Earth has to provide almost everything. This is why mission planners think in layers. They ask what can be sent ahead, what can be made at the destination, what can be reused, what can be left behind, what must return, what must be protected, what can be lighter, what can be smaller. A Mars mission is not just a journey, it is a long argument with mass. If you add more shielding to protect astronauts from radiation, the spacecraft becomes heavier. If it becomes heavier, it needs more propulsion. More propulsion means more propellant, bigger tanks, stronger structures, perhaps more launches. If you reduce the shielding, you may reduce weight, but increase risk. Every improvement seems to tug on another part of the design. It is like trying to tuck in a blanket on one side of the bed and discovering the other side has escaped. For robotic spacecraft, the problem is often easier because robots do not need air, food, water, sleep, privacy, or reassuring conversations when the mission gets stressful. A robotic probe can be small, patient, and extremely tolerant of discomfort. It can spend years coasting through space, wake up for a flyby, take pictures, send data home, and never once complain about the menu. This is why we have been able to explore so much of the solar system with relatively small spacecraft. We launch them carefully, aim them precisely, and often use gravity assist to stretch their capabilities. But humans bring mass. Humans are wonderful, curious, fragile bundles of requirements. We bring meaning to exploration, but also plumbing. The weight problem becomes especially clear when we think about slowing down. Many people imagine space travel as simply going fast enough toward a destination. But arriving is not the same as passing by. If you want to orbit Mars, you must reduce your speed relative to Mars. If you want to land, you need to shed even more energy. If you want to return, you must climb away again. A flyby is easier because the spacecraft does not have to stop. It can rush past, take measurements, wave politely, and continue onward. But a human mission cannot simply wave at Mars through the window and call it a day. To explore, you need to arrive in a usable way. An arrival costs fuel. There are clever tricks. Aerobraking can use a planet's atmosphere to slow a spacecraft, saving propellant. A spacecraft can dip into thin upper air again and again, letting drag gradually reduce its speed. This is elegant, but it requires an atmosphere, heat protection, careful navigation, and patience. Gravity assist can change a spacecraft path without using much fuel, but they require the right planets in the right places at the right times. In spaceflight, cleverness often means using the solar system itself as part of the engine. You borrow from a planet, you lean on an atmosphere, you coast along a path shaped by gravity. These tricks are not cheating. They are what good engineering looks like when the fuel budget is unforgiving. Even so, chemical propulsion keeps bringing us back to the same central issue. It has high thrust but limited efficiency. It can push hard, but it uses propellant quickly. It is excellent for the urgent moments, launch, major burns, landing, emergencies. It is less ideal for the long stretches where what matters is not a dramatic shove, but steady, efficient change. This is why a spacecraft might use a chemical rocket to leave Earth, but a very different kind of engine to travel once it is already in space. The fuel problem is not the same everywhere. On Earth, you need strength. In deep space, you may need patience. Imagine trying to move a heavy wardrobe across a room. One person gives it a mighty shove and it slides a little, then stops because the floor has friction. That is Earth thinking. In space, there is almost no friction, so even a tiny push keeps adding motion. A gentle engine that runs for months can eventually create a large change in speed. It would be useless for lifting off from Earth. It could not overcome gravity quickly enough, but in orbit, away from the ground, that weakness becomes less important. The engine does not need to win a wrestling match with a planet. It only needs to keep whispering in the same direction for a long time. This is why the future may involve separating the idea of launch from the idea of travel. Rockets may take us to orbit, then spacecraft may refuel, assemble, or switch to different propulsion systems. Instead of one vehicle doing everything, future missions may become more like transportation networks. A rocket carries cargo up. A space tug moves it to a higher orbit. A nuclear stage sends it toward Mars. Electric propulsion adjusts the path. A lander handles descent. A surface vehicle handles exploration. This may sound complicated, and it is. But it may also be more realistic than asking a single chemical rocket system to do every job from ground to deep space and back again. The weight problem also encourages us to think about resources beyond Earth. If propellant can be made in space, everything changes. Water from the Moon, asteroids or Mars could potentially be split into useful propellants, or used directly in certain propulsion concepts. Oxygen could be extracted from local materials. Fuel depots in orbit could allow spacecraft to launch with less burden and fill up later. This is sometimes called in-space refueling, and it is one of those ideas that sounds ordinary until you realize how transformative it could be. On Earth, transportation depends on refueling networks. Cars, planes, and ships do not begin every journey carrying all the fuel they will ever need for their entire future. Spacecraft mostly do, and that is part of why space is so difficult. But building a refueling network in space is not easy. You have to launch or produce the propellant. You have to store it, sometimes at extremely low temperatures. You have to prevent it from boiling away. You have to transfer it reliably in weightlessness. You have to create standards, docking systems, safety procedures, and all the unglamorous details that turn a dramatic concept into infrastructure. The future of space travel may depend as much on storage tanks, valves, and orbital depots as on glamorous engines. Space civilization, if it ever grows, may be built not only by astronauts and starships, but by excellent plumbing. Again, space is very often plumbing wearing a helmet. There is also a deeper lesson in the tyranny of fuel. It tells us that energy and mass are not separate concerns. They are bound together in the practical life of every mission. A spacecraft designer is always asking what must move, how fast it must move, how much energy it needs, and where that energy comes from. Carrying energy as chemical fuel is one answer. Using sunlight is another. Using nuclear reactions is another. Receiving energy from a laser beam far away is another. Each method changes the weight problem in a different way. If the spacecraft does not have to carry all its energy, it may become lighter. If it can use a more efficient engine, it may need less propellant. If it can gather resources along the way, it may no longer be trapped by everything launched from Earth. This is why some of the strangest propulsion ideas are really attempts to escape the same old trap. A solar sail tries not to carry propellant at all. It lets light provide the push. A laser sail pushes the idea further, using a powerful beam from elsewhere to drive a spacecraft without onboard fuel. An ion engine carries propellant, but uses it far more efficiently, giving tiny pushes for very long periods. A nuclear engine uses a more energy-rich process to heat or accelerate propellant, reducing the amount needed for a given mission. A space tether exchanges momentum instead of burning propellant in the usual way. Different methods, same desire, to stop letting fuel dominate the design. Of course, none of these alternatives are perfect. Solar sails need large, delicate structures. Ion engines need electrical power and time. Nuclear propulsion raises safety and engineering concerns. Laser propulsion requires enormous infrastructure and precise control. Tethers must survive stresses, orbital mechanics, and the general inconvenience of being very long objects moving very fast. There is no free ride through the universe. Every idea pays somewhere. If not in fuel, then in complexity. If not in complexity, then in cost. If not in cost, then in materials, time, risk, or power. The goal is not to find magic. The goal is to find a better bargain. Rockets gave us the first bargain, and it was a good one. Burn fuel, throw exhaust backward, move forward. It is direct, forceful, and reliable enough to build a space age on. But the farther we want to go, the more that bargain strains. It asks us to carry too much. It makes missions larger, heavier, slower, and more expensive. It turns every ambition into a mass calculation. It makes human exploration beyond the moon possible, but difficult. It makes interstellar travel with ordinary methods effectively unreachable on human timescales. Not because we lack courage, but because courage does not reduce propellant mass. Though it is very useful during meetings, the tyranny of fuel is therefore not a reason to give up. It is a reason to become more clever. It pushes us toward lighter spacecraft, reusable systems, orbital assembly, refueling depots, local resources, efficient engines, and new kinds of propulsion. It teaches us that space travel is not just about building bigger machines. Sometimes it is about carrying less. Sometimes it is about waiting longer. Sometimes it's about using what space already offers: sunlight, gravity, motion, magnetic fields, the materials of other worlds. The future may belong to technologies that understand this better than chemical rockets can. And this brings us gently to the next kind of engine, one that looks almost laughably weak if you judge it by the standards of launch. It does not roar. It does not lift towers from the ground. It does not shake windows or paint the sky with fire. Its thrust can be tiny, almost delicate. But it has one great advantage. It can use propellant with remarkable efficiency, turning small amounts of matter into long, patient acceleration. In the quiet emptiness of space, where nothing slows you down except gravity and time, that kind of weakness can become a different form of strength. A tiny push can seem almost useless at first. On Earth, we are surrounded by friction, weight, air, hills, roads, floors, and all the familiar stubbornness of ordinary objects. If you want to move a heavy table across a room, a gentle tap will not impress it. If you want to lift a suitcase, whispering encouragement at it is rarely enough, though it may make the suitcase feel emotionally supported. We're used to force being obvious. We expect useful engines to roar, rumble, spin, burn, or at least make some kind of confident mechanical noise. Rockets match that expectation perfectly. They are loud, they are bright, they make motion feel dramatic. Ion engines are different. Electric thrusters are different. They do not arrive in the imagination like thunder. They are quiet, delicate, and patient. Instead of producing a huge blast for a few minutes, they produce a small push for a very long time. If a chemical rocket is a sprinter leaping from the starting line, an ion engine is someone walking calmly through the night, step after step, never stopping, never showing off, and eventually reaching a distance that the sprinter could not sustain. That is why these engines matter so much for the future of space travel. They are not built for the launch pad. They are built for the long road after the launch pad has vanished behind us. The basic idea is surprisingly elegant. Instead of burning fuel in the chemical sense, an electric thruster uses electrical energy to accelerate tiny particles and send them out the back of a spacecraft. Those particles may be ions, which are atoms that have been given an electric charge. Once charged, they can be pushed by electric or magnetic fields. The engine guides them, accelerates them, and throws them away at very high speed. The spacecraft moves in the opposite direction, so the old rocket bargain still exists. Something goes backward, the spacecraft goes forward. But the way the engine spends its propellant is very different. In a chemical rocket, the energy comes from the propellant itself. Fuel and oxidizer react, hot gas expands, and exhaust rushes out of the engine. It is powerful, but it uses propellant quickly. In an electric thruster, the propellant is more like material to be pushed, while the energy comes from electricity. That electricity might come from solar panels near the sun, or from a nuclear power source farther out. Because the engine can accelerate small amounts of propellant to very high speeds, it can use that propellant much more efficiently than a chemical rocket. It does not throw out a lot of mass slowly. It throws out a little mass very quickly. The result is a gentle push that can last for months or years. This is the strange trade. Electric propulsion is efficient but weak, very weak compared with launch rockets. An ion engine could not lift a spacecraft off Earth. It could not rise from a launch pad. It could not fight gravity and atmosphere in the way a chemical rocket does. Trying to launch from Earth on an ion engine would be a little like trying to escape quicksand by politely exhaling through a straw. The push is real, but not enough for that job. On the ground, it would be hopeless. In space, however, the rules change. There is no air resistance to overcome. There is no road friction. Once a spacecraft is moving, it keeps moving. A tiny push, repeated constantly, begins to matter. This is one of the most beautiful differences between Earth travel and space travel. On Earth, engines often have to keep fighting the environment. A car engine keeps working because the road, air and rolling resistance keep stealing motion. A plane engine keeps working because the aircraft must keep pushing through air. In deep space, if you give a spacecraft a push, it does not quickly slow down just because the engine stops. It coasts. Gravity may bend its path, but empty space does not act like a sticky floor. So an engine that gives a small push for a long time can gradually build up a large change in motion. The spacecraft may begin slowly, almost lazily, but over time the effect grows. This is why electric propulsion feels almost backwards to our instincts. We're used to judging engines by how hard they shove right now. But for many deep space missions, the more important question is how efficiently they can keep changing a spacecraft's path over time. An ion engine might produce a push so small you could barely feel it if it was somehow attached to your hand. But if it runs day after day, week after week, month after month, the spacecraft keeps gaining speed. The acceleration is tiny, but it does not need to be large. It needs to be persistent. Space rewards persistence in a way that Earth rarely does. The glow of an ion engine is also different from the flame of a chemical rocket. Instead of a roaring plume of fire, many electric thrusters produce a soft blue or violet glow, depending on the propellant and the design. It looks less like an explosion and more like a laboratory secret. There is something almost calm about it. A spacecraft using ion propulsion does not seem to be forcing its way through the universe. It seems to be quietly persuading itself to move. The engine hums in silence, particles stream away, and the spacecraft slowly adjusts its path across millions of kilometers. One of the most famous propellants for ion engines has been xenon, a heavy noble gas. Xenon is useful because it is relatively easy to ionize, dense enough to store reasonably well, and heavy enough that each ion carries useful momentum when accelerated. It is not the only possible propellant, but it has been a favourite for many missions. The word noble gas makes it sound as if xenon should be wearing a tiny crown and refusing to mix at parties, which is not entirely wrong chemically speaking. Noble gases are famously unreactive, and in this case that stability is useful. The engine does not need xenon to burn. It needs xenon to become charged and then be flung away. There are several kinds of electric thrusters. Some use grids to accelerate ions. Some use magnetic fields and plasma. Some are called Hall thrusters, which have become common for satellites. Others are more experimental. The details can become wonderfully technical very quickly, and if we wandered too far into them, we might need a cup of tea and a very patient diagram. But the shared idea is that electricity is being used to give propellant a much higher exhaust speed than chemical reactions usually allow. That high exhaust speed means less propellant is needed for the same overall mission change, and that is the key advantage. For satellites around Earth, electric propulsion has already become extremely valuable. Many satellites use electric thrusters to adjust their orbits, maintain position, or gradually move from one orbit to another. Communication satellites, for example, may use electric propulsion to stay in the right place above Earth, or to reach their operating orbit after launch. Because the system uses less propellant, the satellite can either be lighter or carry more useful equipment. Less mass spent on fuel means more mass available for instruments, antennas, power systems, or simply longer mission life. In space engineering, that is not a small benefit. It is often the difference between a mission that works comfortably and a mission that has to count every gram like a nervous baker measuring flour. Electric propulsion has also proved itself beyond Earth orbit. Robotic spacecraft have used ion engines for ambitious deep space missions. These engines allowed spacecraft to change course over long periods, visit multiple targets, and stretch mission possibilities beyond what a chemical propulsion system of the same mass could easily do. The key is not dramatic speed at the beginning. The key is flexibility over time. An ion-powered spacecraft can slowly reshape its orbit, adjust its trajectory, and keep working after a chemical system would have spent most of its propellant. It is a quiet form of freedom. There is a lovely lesson here about pace. A chemical rocket makes its decision quickly. It burns, it changes speed, and then it coasts. An ion engine makes its decision gradually. It keeps nudging. It can keep adjusting. It can turn a long journey into a continuous act of steering rather than a few brief moments of impulse. This can make mission planning very different. Instead of one large push followed by a long coast, the spacecraft can follow a more slowly evolving path. Its route may be shaped over time, almost like a brushstroke across the solar system rather than a thrown stone. But of course, there are limitations. Electric thrusters need power. Near Earth and the inner solar system, solar panels can provide that power. Sunlight is strong enough to be useful, and large solar arrays can feed the engine over long durations. But as the spacecraft travels farther from the Sun, sunlight becomes weaker. Out near Jupiter, Saturn, or beyond, solar power becomes more difficult. You can build larger panels, but panels have mass, and mass is always waiting in the corner with a clipboard. At some point, nuclear electric power becomes more attractive. A nuclear reactor could provide electricity for thrusters far from the Sun, allowing electric propulsion to operate in darker regions of the solar system. That idea is powerful, but it adds complexity, safety concerns, heat management, and engineering challenges. Another limitation is time. Electric propulsion is efficient, but it is not always fast in the way people imagine. Because the thrust is low, it can take a long time to build up speed or change orbit. For cargo, that may be fine. A shipment of equipment sent ahead to Mars does not get bored. A robotic probe does not mind spending years spiraling outward. But humans are less patient, and more importantly, humans are fragile. A crewed spacecraft cannot always afford extremely long travel times. Astronauts need protection from radiation, reliable life support, food, exercise, medical care, and mental well-being. A very slow journey may save propellant but increase other risks. Space travel is rarely about solving one problem. It is about choosing which problems you prefer to have. This means electric propulsion may be ideal for some roles and unsuitable for others. It may be excellent for moving cargo through space slowly and efficiently. It may be excellent for satellite station keeping and deep space robotic missions. It may be useful for parts of a crewed mission, especially once a vehicle is already assembled in orbit. But it is not a simple replacement for chemical rockets. You would not put an ion engine under a crew capsule on the surface of Earth and expect a graceful liftoff. The engine would glow softly, the spacecraft would remain exactly where it was, and everyone watching would have time to reconsider the plan. Still, the weakness of electric thrusters should not make us dismiss them. Weakness depends on context. A feather is weak against a locked door but very useful to a bird. An ion engine is weak against Earth gravity, but useful in the long quiet of space. That is the deeper point. The future of space travel may not be about finding one perfect engine to do everything. It may be about matching engines to environments, chemical rockets for launch, electric thrusters for efficient cruising and orbital work, nuclear systems for high-energy missions, sails for propellantless acceleration. Each technology has a place, a range, a temperament. There is also something philosophically interesting about ion propulsion. It changes the emotional picture of exploration. The old image of space travel is explosive. A rocket launches, engines blaze, a spacecraft streaks away. Electric propulsion offers another image. A spacecraft leaves Earth on a conventional rocket, reaches the silence above, unfolds its solar panels, wakes its electric engine, and begins the long, slow push. No dramatic blast, no sudden leap, just patient acceleration under a thin blue glow. It is almost sleepy, in the best possible way. a machine moving through darkness by persistence rather than force. That may be exactly what deep space requires. The solar system is not a short hallway. It is a vast set of distances where small efficiencies become enormous over time. Saving propellant means more science instruments, more cargo, longer missions, more flexible routes. The advantage is not always speed. Sometimes the advantage is endurance. A spacecraft that can keep maneuvering after years in space is more capable than one that spent its fuel early and now has only gravity to guide it. Electric propulsion gives mission designers options, and options are precious when the nearest repair shop is millions of kilometers away. Ion engines also invite us to rethink what powerful means. A launch rocket is powerful because it does a huge amount of work quickly. An electric thruster is powerful because it uses its resources carefully and keeps working. One is a shout, the other is a steady voice. In daily life, we often celebrate the shout, but space has plenty of room for the steady voice. A whisper that lasts long enough can cross a solar system. There are even more advanced electric propulsion ideas being studied. Some concepts use stronger power sources to increase thrust. Some use plasma in different ways. Some imagine nuclear electric spacecraft that generate large amounts of electricity and feed powerful thrusters for missions to Mars or the outer planets. Such vehicles could become workhorses of deep space transportation, especially for cargo. Instead of launching everything in one dramatic chemical push, future mission planners might send supplies, habitats, fuel and equipment slowly ahead using electric propulsion. By the time humans depart, the things they need could already be waiting. This would not make space travel easy, but it could make it less dependent on one enormous launch, and more like a planned sequence. There is a quiet practicality in that vision. Not every spacecraft needs to be fast. Some can be patient. Some can take the scenic route. Some can spend years slowly climbing from one orbit to another, carrying cargo that does not complain, does not age in the biological sense, and does not ask whether we are there yet. Human missions could then focus on shorter travel times and safer designs, while electric cargo ships do the slow, heavy work in advance. The future of space may involve many kinds of vehicles moving at many different paces, like a harbour where tugboats, cargo ships, ferries, and research vessels all share the same water. And yet, even if electric propulsion becomes common, it does not fully solve the dream of rapid human travel to Mars, let alone the stars. Efficiency is not the same as speed. To move large, crewed spacecraft quickly, we may need engines that combine better efficiency with higher thrust. That is a difficult combination. Chemical rockets give high thrust but use propellant quickly. Ion engines use propellant well but push gently. The ideal future engine would somehow do both, push hard and waste little. Nature rarely hands out that combination cheaply. When engineers search for it, they begin looking toward more energetic sources, and one of the most obvious is nuclear power. Before we go there, it is worth lingering for a moment on the image of the ion engine itself. A small device quietly accelerating charged particles, barely pushing by earthly standards, yet able to guide a spacecraft across enormous distances. It is not the kind of engine that wins attention in a launch broadcast. It will not rattle windows or fill the sky with smoke. But in the long silence between planets, it becomes one of the most elegant tools we have. A reminder that the future of travel may not always belong to the loudest machines. Sometimes it belongs to the patient ones, the ones that understand that space is wide, time is long, and even the smallest push can become a journey if it lasts long enough. There is a particular kind of impatience that appears whenever we talk about Mars. Not ordinary impatience like waiting for toast or watching a file slowly download while pretending to be calm. This is a deeper impatience, the kind that comes from knowing a world is nearby in the grand scale of astronomy, and yet still painfully far away in the scale of human travel. Mars is right there, at least compared with the outer planets and the stars. It is our neighbour, our red companion, a cold desert world that has followed Earth around the Sun for billions of years. Through telescopes, spacecraft cameras, and rover tracks, it has become familiar enough to feel almost reachable, and then the travel time reminds us that almost is doing a great deal of work. With the kinds of chemical rockets we use today, a journey to Mars is usually measured in months, not days, not a quick hop, months. A crewed spacecraft would have to cross deep space while carrying people, supplies, life support, radiation protection, equipment, spare parts, and every little system needed to keep fragile human bodies alive in a place that does not naturally provide air, water, warmth, gravity, or much sympathy. During that time, astronauts would be exposed to cosmic radiation and solar storms. Their muscles and bones would weaken in weightlessness unless carefully exercised. Their spacecraft would have to function continuously, with no convenient garage to pull into if something made a suspicious noise. The faster we can make that trip, the safer and more practical Mars exploration becomes. This is where nuclear propulsion begins to enter the story. It is one of those ideas that sounds both futuristic and oddly old-fashioned. Futuristic because it suggests a deeper, more powerful way to travel through space. Old-fashioned because scientists and engineers have been thinking about it for many decades. Nuclear propulsion is not a sudden new fantasy. It is a long-standing possibility that has waited at the edge of the space age, sometimes studied intensely, sometimes set aside, always quietly present like an engine in the next room that no one has quite decided to start. The appeal is simple. Chemical rockets get their energy from chemical reactions. Fuel and oxidizer combine, release heat, and produce exhaust. This works beautifully, but the amount of energy available from chemistry is limited. Nuclear reactions release far more energy from a much smaller amount of material. That does not mean a nuclear spacecraft is automatically easy, safe, or cheap. Nothing in space is automatically anything except complicated. But it does mean nuclear energy offers a way to change the bargain. If chemical rockets are limited by how much energy they can release from propellant, then nuclear systems might let us heat or accelerate propellant more effectively, using less mass for a greater result. The most discussed near-term idea is nuclear thermal propulsion. The phrase may sound severe, but the basic picture is not too difficult. Instead of burning fuel with an oxidizer, a nuclear reactor produces heat. A propellant, often imagined as hydrogen, passes through or around the hot reactor core. It becomes extremely hot and rushes out through a nozzle, pushing the spacecraft forward. The propellant is still being thrown backward, so the familiar rocket principle remains. But the energy heating that propellant comes from nuclear fission rather than chemistry. The result could be an engine that uses propellant more efficiently than a chemical rocket, while still producing enough thrust to be useful for major space maneuvers. That last part matters. Ion engines are wonderfully efficient, but they push gently. Chemical rockets push hard, but burn through propellant quickly. Nuclear thermal propulsion sits in an interesting middle ground. It could offer stronger thrust than many electric systems and better efficiency than chemical rockets. For a Mars mission, that combination is very tempting. It might shorten the time between planets. It might allow more flexible departure windows. It might reduce the total amount of propellant needed for certain mission designs. It might make a crewed Mars journey feel less like balancing every hope on the thinnest possible fuel budget. Of course, once the word nuclear appears, the room becomes very attentive. People do not hear nuclear and think, how relaxing. They think of reactors, radiation, accidents, weapons, waste, and long technical discussions with diagrams nobody wants near a bedtime snack. That caution is understandable. Nuclear technology carries real responsibilities. A nuclear propulsion system would have to be designed with extraordinary care. It would likely not be used to launch directly from Earth like an ordinary first stage. The more realistic picture is that chemical rockets would still lift the spacecraft or its components into orbit, and the nuclear engine would be used once safely in space. That way, the reactor could remain inactive during launch, and only be started when it is already far from Earth's surface. Safety would shape every part of such a system. The reactor would need to survive launch loads. It would need to remain secure in the unlikely event of a launch failure. It would need shielding to protect the crew. It would need cooling and control systems. It would need materials that can endure extreme heat without cracking, melting, or behaving like a dramatic villain in the final act. Heat is not a small detail in nuclear propulsion. Heat is the whole point, and also one of the great challenges. The engine must get very hot to perform well, but the spacecraft must not become a flying furnace with passengers. This is one of the central engineering tensions. A nuclear thermal engine works best when it can heat propellant to very high temperatures. Higher temperatures can mean better performance, but high temperatures are hard on materials. The reactor core must keep its shape and function while propellant rushes through it. It must handle radiation, vibration, thermal stress, and repeated operation. The engine is not just a reactor and not just a rocket. It is both at once, which is a little like combining a fireplace, a pressure cooker, and a violin, then asking it to perform flawlessly in vacuum. Another challenge is hydrogen. Hydrogen is attractive as a propellant because it is very light, and light propellant can be accelerated efficiently. But hydrogen is also inconvenient. It must be stored at extremely low temperatures if kept as a liquid. It can leak through tiny gaps. It takes up a lot of volume. It requires large insulated tanks, and those tanks add mass. Spacecraft designers enjoy hydrogen in the same way a chef might enjoy a delicate ingredient that improves the dish, but spills everywhere, spoils quickly, and insists on being stored in a special silver box at midnight. Useful, yes. Effortless, no. Still, the potential benefits are serious enough that nuclear thermal propulsion continues to attract interest. For Mars, even shaving weeks or months from a journey could matter. Less travel time means less radiation exposure. It means less time in weightlessness. It means fewer supplies consumed in transit. It may give mission planners more options if conditions change. A spacecraft with stronger and more efficient propulsion could have a wider range of possible paths rather than being locked into the slow patience of traditional transfers. In space exploration, flexibility can be as valuable as speed. A mission that has choices is safer than one that must follow a narrow path and hope everything behaves. There is also nuclear electric propulsion, a related but different idea. Instead of using a reactor to heat propellant directly, a nuclear reactor could generate electricity. That electricity would then power electric thrusters, such as ion or plasma engines. This would not usually give the same high thrust as nuclear thermal propulsion, but it could provide efficient long-duration propulsion far from the sun. Solar electric propulsion depends on sunlight, and sunlight weakens with distance. A nuclear electric spacecraft could keep producing power in the darker regions of the solar system, pushing patiently toward the outer planets, or moving heavy cargo through deep space. In this version, nuclear power becomes less like a blast of heat and more like a steady power plant for a long voyage. For crewed Mars missions, nuclear thermal propulsion often gets the spotlight because it promises relatively high thrust and shorter travel times. But nuclear electric propulsion could be useful in a broader transportation system. Imagine cargo ships moving slowly and efficiently between Earth orbit, Mars orbit, lunar orbit, and perhaps asteroid resources. They do not need to be fast in the human sense. They need to be reliable. A nuclear electric tug could spend years moving supplies, habitats, fuel, and equipment where they are needed. It might not look heroic, but the future of exploration may depend heavily on machines that do quiet work long before astronauts arrive. That is a theme worth noticing. Space exploration is often imagined as the brave crew leaving Earth in one magnificent vehicle. But real exploration may become more like building a network. Supplies sent ahead, fuel waiting in orbit, habitats assembled before the crew arrives, cargo moving slowly on efficient engines, crewed vehicles taking faster paths, landers and ascent vehicles staged at destinations. nuclear propulsion could become part of that network, not necessarily the single grand solution to everything, but a powerful tool in the growing toolkit of deep space travel. There is also the question of public trust. Even if engineers design a nuclear propulsion system that is safe by careful standards, people must accept it. Space programs do not exist in a vacuum, even when their spacecraft do. They exist inside politics, budgets, public opinion, environmental concern, and international agreements. A nuclear rocket might be technically impressive and still face opposition if people do not feel the risks are clearly explained and responsibly managed. The history of spaceflight is filled with machines, but also with confidence. People have to believe that the mission is worth doing and that those doing it understand the dangers. With nuclear propulsion, that trust would be especially important. It is easy to imagine the nervous headlines. Nuclear engine headed for orbit. Reactor to power Mars ship. Atomic rocket tested for future crewed mission. Even if the reality is more controlled than the headline suggests, the emotional reaction is predictable. And perhaps that is not a bad thing. Technologies with serious risks deserve serious questions. The goal should not be to wave away concern, but to answer it. How is the reactor launched? When is it activated? What happens if the launch fails? How is radiation shielded? How is the engine tested? What materials are used? What international standards apply? A mature spacefaring civilization would need not only better engines, but better conversations about engines. The idea of nuclear propulsion also changes our sense of scale. Chemical rockets made reaching orbit possible. Nuclear propulsion points toward a stage where travel between planets becomes less like a one-time stunt and more like a difficult but repeatable route. Mars would still be hard. It would still be dangerous. The planet would still be cold, dry, dusty, and unwelcoming in the way only a world without breathable air can be. But faster propulsion could reduce some of the journey risk and make mission planning less brittle. The road to Mars might become shorter, not because Mars moves closer, but because our engines become better matched to the distance. There is a comfort in remembering that every major transportation leap required a new relationship with energy. Sailing ships used wind, steamships burned coal, trains reshaped continents by carrying their own power, aircraft used engines light enough and strong enough to turn air into lift and distance into schedule. Rockets use chemical energy to break the grip of Earth. Each step was not just a new vehicle, but a new bargain with nature. Nuclear propulsion would be another bargain. A way of saying that if chemistry opened the door to space, perhaps nuclear energy can help us move through the hallway beyond it. But nuclear propulsion is not a magic shortcut to the stars. It would not make Mars easy. It would not remove the need for life support, radiation shielding, careful navigation, entry systems, surface habitats, return plans, and all the quiet details that keep a mission from becoming a very expensive lesson. It would not let us ignore orbital mechanics or launch windows. It would not turn space into an ocean with friendly harbours every few miles. It would simply improve part of the problem. A crucial part, yes, but still one part. Space travel is so difficult that even a powerful improvement can feel modest once it is folded into the whole mission. For interstellar travel, nuclear propulsion becomes more complicated. Nuclear thermal engines might help within the solar system, but reaching another star in a human lifetime would demand speeds far beyond ordinary Mars missions. More advanced nuclear ideas, like fusion propulsion, have long been imagined as possible paths toward much faster spacecraft. Fusion is the process that powers stars, and if humans could use it in a controlled engine, it might offer far greater performance than fission-based systems. But fusion propulsion remains a much harder challenge. Controlling fusion for practical power on Earth is difficult enough. Turning it into a reliable spacecraft engine is another level of ambition. It belongs to the edge of a long-term possibility, not the next obvious step. Even so, the presence of nuclear ideas in spaceflight reminds us that the future will probably not be built from one technology. Chemical rockets may lift us from planets. Nuclear thermal engines may shorten the road to Mars. Nuclear electric systems may move cargo and robotic explorers through deep space. Fusion, one day perhaps, may open faster routes to the outer solar system or beyond, and alongside all of these, other methods may help reduce the need to carry propellant in the first place. The story is not rockets versus nuclear propulsion. It is a gradual expansion of methods, each one answering a weakness in the one before it. What makes nuclear propulsion especially compelling is that it speaks directly to the human problem of Mars. The Red Planet is not merely a target for robots. It is the first place beyond the Moon where people seriously imagine living and working for long periods. A faster road matters because human bodies are not machines that can be powered down for the trip and restarted on arrival. We carry fear, boredom, hope, digestion, muscles, bones, sleep cycles, and the occasional need for privacy. The spacecraft must support all of that. Every extra day in transit adds demands. Every shorter journey removes some pressure. In that sense, propulsion is not just about speed. It is about health, safety, mission design, and the emotional reality of sending people far from home. There is something quietly moving about that. Nuclear propulsion sounds technical, but beneath the engineering is a very human wish. We want the distance to be less punishing. We want explorers to spend less time in the dangerous emptiness between worlds. We want Mars to be reachable not just by heroic sacrifice, but by practical systems that can be improved, repeated, and trusted. We want the journey to become less like a dare and more like a route, still difficult. Still awe-inspiring, but less dependent on accepting months and months of exposure simply because our engines cannot do better. And perhaps that is the real promise. Not a sudden golden age of effortless travel, but a step toward a more mature kind of spaceflight. Chemical rockets gave us access. Electric thrusters gave us patience. Nuclear propulsion may offer speed and endurance in a new balance. It may let us carry heavier payloads, choose better paths, and reduce the time crews spend between worlds. It may help turn Mars from a distant dream into a destination that can be planned with more confidence. The engine itself would not be glamorous in the way a launch is glamorous. It would do its work in vacuum, far above the crowds, after the cameras have already watched the chemical rockets rise. But out there, in the dark between Earth and Mars, it could become the difference between a journey that feels barely manageable and one that begins to feel like the first version of a real road. Still, even nuclear propulsion keeps the old pattern alive. It carries propellant, it carries machinery, it still throws something backward to move forward. It improves the bargain, but it does not completely escape it. And that is why the imagination keeps moving towards stranger possibilities. What if a spacecraft could travel without carrying much propellant at all? What if sunlight could push it? What if a long tether could exchange motion like a handoff in orbit? What if the journey could use the environment instead of bringing every ounce of movement from home? After fire, after ions, after the atom, space travel begins to look toward methods that are quieter still, methods that borrow from light, gravity, and motion itself. At first, the idea of travelling through space without carrying fire sounds almost too gentle to be useful. We are so used to imagining spaceflight as a matter of engines, fuel tanks, roaring exhaust, and controlled violence that anything quieter feels suspicious. A spacecraft should burn something, surely. It should throw flame behind it. It should have pipes, pumps, pressure, and at least one part that makes engineers stand with folded arms and very serious expressions. Yet some of the most interesting ideas for deep space travel begin by asking a calmer question. What if the spacecraft did not need to carry all of its push inside itself? What if space itself offered things we could lean on? That is the promise behind solar sails and space tethers. They are not rockets in the familiar sense. They do not depend on burning fuel in a chamber. They do not rise from Earth on their own. They do not shake the ground. They belong to the part of the journey after the launch, when the spacecraft is already above the atmosphere, already free of roads and oceans and runways, already moving through the wide silence where small influences can build into meaningful travel. These systems try to solve the old weight problem by changing the question. Instead of asking how much propellant can we carry, they ask how much propellant can we avoid carrying at all. Solar sails are perhaps the most charming version of this idea, partly because the name sounds like something from both an ancient harbour and a future starship yard. A sail is one of the oldest tools of travel. Long before engines, long before aircraft, long before rockets, human beings crossed seas by using the wind. A sail did not create the wind, it used what was already there. It turned a natural flow into motion. A solar sail does something similar, but instead of catching moving air, it catches light. Not wind from the atmosphere, but sunlight itself. This may sound strange, because light does not feel like it pushes. You do not step outside on a sunny morning and get shoved politely into the flower beds. Sunlight warms your face, brightens windows, fades curtains, and occasionally reveals dust you were happier not knowing about. But light carries momentum. It can exert pressure, extremely tiny pressure, when it strikes a surface. On Earth, that pressure is overwhelmed by gravity, air, friction, and the ordinary business of living on a planet. In space, with a large enough reflective sail and enough time, the push from sunlight can matter. The push is very small, that should be said clearly. A solar sail is not a fast launch system. It will not lift from a pad. It will not thunder toward orbit. It cannot compete with a chemical rocket when you need immediate force. But once in space, a sail can keep receiving sunlight without carrying fuel. The spacecraft does not need to burn propellant to gain that gentle acceleration. The sun keeps shining. The sail keeps feeling that tiny pressure. Day after day, week after week, month after month, the effect accumulates. It is the same lesson we saw with ion engines, but in an even more radical form. A small push can become useful if it lasts long enough. The sail itself must be extremely light and very large. This is one of the central challenges. A solar sail has to spread over a wide area to collect enough light pressure, but it cannot be heavy, because a heavy sail defeats the purpose. It must be thin, reflective, strong enough to deploy, stable enough to control, and durable enough to survive the environment of space. It may face temperature changes, radiation, micrometeoroids, and the simple difficulty of unfolding a huge sheet in vacuum without tangling it, like a bedsheet on laundry day. Anyone who has struggled to fold a fitted sheet can perhaps feel a tiny sympathy for spacecraft engineers. Control is also important. A sail is not simply opened and forgotten. By changing its angle relative to the sun, a spacecraft can adjust the direction of the push. It can spiral inward toward the sun or outward away from it. It can slowly change its orbit. It can use sunlight not as a direct highway, but as a continuous influence. The motion is subtle, guided over long periods. The spacecraft becomes less like a thrown object and more like a sailor reading conditions, adjusting the sail and letting a steady natural force shape the journey. There is something practical and beautiful in that, but it is not magic. Solar sails work best where sunlight is strong. Near Earth and closer to the sun, the pressure of light is more useful. Farther out, sunlight weakens, and the push becomes much smaller. A solar sail headed to the outer solar system would need patience, clever trajectories, or perhaps help from other methods. Also, the sail is large and delicate, which can make it difficult to package, launch, deploy, and steer. The very thing that gives it power, a wide surface, also makes it vulnerable. A solar sail is not a roaring beast. It is a disciplined sheet of material, and sheets of material have their own quiet ways of making life complicated. Still, solar sails change the imagination of space travel. They offer the possibility of movement without carrying propellant for that movement. This matters deeply. If a spacecraft can use sunlight, it can save mass. Saved mass can become instruments, communications equipment, shielding, or simply lower launch cost. For small robotic probes, especially sails may provide long-term maneuvering that would otherwise require fuel. They could help spacecraft hover in unusual positions, study the sun, monitor space weather, or move through the inner solar system in ways that would be difficult using only chemical propulsion. There is also the possibility of using sails with beams of light from elsewhere. If sunlight is too weak or too spread out for very high speeds, a powerful laser could, in theory, provide a much stronger push. That idea takes us toward later possibilities, especially for tiny probes sent toward other stars. But the underlying principle is already present in the solar sail. The spacecraft is not carrying the energy source in the usual way. It is being pushed by something outside itself. That is a profound shift. It makes the vehicle lighter, but it moves complexity elsewhere. Instead of carrying fuel, you may need a huge sail or a powerful beam or precise aiming across enormous distances. Again, the universe does not give free rides. It simply lets us choose which difficulty we prefer. Space tethers approach the same problem from a different direction. If solar sails borrow momentum from light, tethers can borrow from motion, gravity, and orbital mechanics. A tether is, in simple terms, a long cable in space. That may sound disappointingly plain after nuclear engines and glowing ion thrusters, but do not be fooled. A long cable moving in orbit can do surprisingly interesting things. It can connect two masses, exchange momentum, generate electricity under certain conditions, change orbits, or even act like a rotating sling that catches and releases spacecraft. Space tethers are one of those ideas that seem simple until you start thinking about them, and then they become delightfully strange. The easiest version to picture is a rotating tether. Imagine a long cable spinning in space, with a hub or counterweight at its centre. The ends of the tether move in large circles. If a spacecraft meets the lower end at the right moment, the tether can catch it, swing it around, and release it at higher speed or onto a different path. It is a little like a giant orbital handoff. The spacecraft gains energy and momentum from the tether system. The tether in turn loses some of its own orbital energy unless it is reboosted later. Nothing is created from nothing, but the advantage is that the spacecraft may not need to burn as much propellant for the change. The tether system acts as infrastructure, doing some of the work again and again. This is where space travel begins to look less like individual missions and more like transportation architecture. A rocket is a self-contained event. It launches, burns, stages, delivers, and often ends its role. A tether is more like a road, a bridge, or a port facility. It stays in space and helps many vehicles move. If built and maintained, it could reduce the fuel needed for repeated trips between orbits, or between the Moon and Earth, or perhaps within a future network around Mars. The first time you build such a system, it may be difficult and expensive, but if it can serve many missions, it changes the long-term picture. It is not just propulsion, it is infrastructure. Another kind of tether is electrodynamic. This uses a long conductive cable moving through a planet's magnetic field. As it moves, electric currents can be generated in the tether, and those currents interact with the magnetic field to create forces. Depending on how the system is used, it can help raise or lower an orbit without conventional propellant, or generate electrical power while changing the spacecraft's motion. This sounds almost like cheating, but it is not. It is using the environment. Earth has a magnetic field. A conductor moving through that field can interact with it. The spacecraft pays by changing its orbit or by using electrical power. The physics is real, even if the image of a spacecraft trailing a long electric rope through the invisible magnetism of Earth sounds like something a sleepy inventor might sketch at midnight. Tethers also raise difficult engineering problems. Long cables in space must be strong, light, and resistant to damage. They must survive tension, temperature changes, impacts from tiny debris, and the challenge of deployment. A tether might be kilometers long, perhaps much longer in some concepts. Deploying such a thing is not like unrolling a garden hose. It must be controlled carefully because a cable in orbit is not just hanging there. It is moving, flexing, rotating, and responding to gravity. A tangled tether could be a serious problem. A snapped tether could create debris. A tether that interacts badly with surrounding objects could become a hazard. Space infrastructure is powerful only if it is reliable. Materials matter enormously. Strong lightweight fibers, advanced composites, and clever designs are essential for ambitious tether concepts. The cable must handle forces without becoming too massive. Once again, mass returns with its clipboard. A tether meant to help solve the weight problem must not become so heavy that launching and maintaining it becomes impractical. Every futuristic transport idea eventually meets the same quiet judge. How much does it weigh? How hard is it to build? How often can it be used? How badly does it fail when something goes wrong? Engineering is where beautiful concepts become honest. Still, the attraction of tethers is strong because they suggest a future where not every spacecraft carries all the energy it needs for every maneuver. A tether could pass momentum from one object to another. It could help move cargo. It could reduce propellant use for orbital transfers. In a mature space economy, tethers might work alongside refueling depots, electric tugs, lunar resources, and reusable landers. They would not replace rockets entirely. They would make rockets less lonely. Instead of one vehicle doing everything, a spacecraft could move through a chain of assistance, like a traveller using trains, ferries, elevators, and walking paths, rather than carrying an entire highway in a backpack. One of the most fascinating tether ideas is a space elevator, though it is much more challenging than shorter orbital tethers. A space elevator would be a long cable stretching from Earth's surface up to a counterweight far beyond geostationary orbit, allowing climbers to travel into space without rockets. It is an idea that has inspired many people because it sounds so clean and direct. Step into a climber, rise along a cable, arrive in orbit. No launch flame, no staging, no thunder. Perhaps even fewer nervous countdowns. But for Earth, the material strength required is extraordinary. The cable would have to support its own weight over an enormous length while surviving weather, radiation, impacts, and stresses. We do not currently have a practical material system ready for that job. However, space elevators may be more realistic on smaller worlds with weaker gravity, such as the Moon or Mars. Their lower gravity makes the material challenge easier. A lunar elevator, for example, could help move materials from the Moon's surface to space, supporting future construction, fuel production, or transport networks. A Martian tether or elevator concept might help with cargo movement between surface and orbit. These ideas are far from simple, but they show the direction of thought. If leaving Earth is too hard to do without rockets, perhaps other worlds can become places where non-rocket transport systems are easier to build. This is important because the future of space travel may not be centered only on Earth. Earth is a hard place to launch from. It has strong gravity and thick air. The Moon has low gravity and no atmosphere. Asteroids have even weaker gravity. Mars has lower gravity than Earth and a thin atmosphere. Each place may call for different transport methods. Chemical rockets dominate because Earth is the starting point. But once humans and machines are already in space, the best tool may depend on the local environment. Solar sails near the Sun, tethers in orbit, electrodynamic systems near magnetic planets, nuclear engines for fast transfers, electric propulsion for long efficient cargo routes. The future may be less like one grand vehicle and more like a toolbox spread across the solar system. Solar sails and tethers both teach a similar lesson. Deep space travel may require us to stop thinking only in terms of onboard power. The old model is heroic and self-contained. A spacecraft carries fuel, engines, supplies, and fate. The new model is more ecological, in a technical sense. It asks what forces are already present. Sunlight, magnetic fields, orbital motion, gravity, existing infrastructure. The spacecraft becomes part of a system rather than a lone firework. That may not sound as dramatic, but it's often how transportation matures. Early travel is daring and self-contained. Later travel depends on roads, ports, stations, signals, schedules, repair yards, and shared standards. No one flies across the world today by building a personal airport at both ends. We use infrastructure. There is a gentle humility in this shift. Rockets are about overpowering the first barrier. They are necessary because Earth does not let go easily. Sails and tethers are about cooperation. A sail cooperates with light. A tether cooperates with motion and gravity. Instead of carrying all the fire, the spacecraft finds a way to use what is already there. This does not make the journey easy, but it changes its character. It becomes less about one huge act of burning and more about patient interaction with the environment. Space becomes not empty, but usable. Not friendly exactly, but full of quiet opportunities. Of course, these methods are not enough for every mission. A solar sail cannot land a heavy crewed vehicle on Mars. A tether cannot simply appear wherever needed without being built and maintained. A space elevator is not around the corner waiting for passengers with little rolling suitcases. These technologies will not make rockets vanish. But they can reduce how often rockets must do everything. They can save propellant. They can make repeated routes more practical. They can move cargo, adjust orbits, and open mission designs that would otherwise be too expensive in fuel. They belong to a future where space travel becomes not just possible, but organized. There is also something emotionally different about them. A rocket launch makes you look up and feel the force of escape. A solar sail makes you imagine quiet sunlight touching a vast reflective surface, gently changing a path over months. A tether makes you imagine orbital machinery catching and releasing vehicles with the timing of a careful clock. These are not replacements for wonder, they are different forms of wonder. Less thunder, perhaps, but more patience. Less fire, but more cleverness. And space, with its enormous distances, may reward clever patience more than any single burst of power. As we think about Mars, the outer planets, and beyond, these ideas begin to form a pattern. Chemical rockets help us leave Earth. Nuclear propulsion may shorten major journeys. Electric thrusters can push efficiently for long periods. Solar sails avoid propellant by using light. Tethers use motion and infrastructure to move spacecraft in new ways. Each method chips away at the tyranny of fuel. None of them removes all difficulty. But together they show that the future of space travel may be built from many small escapes from the old bargain. Carry less. Use more. Burn only when burning is truly needed. And once we accept that a spacecraft does not always need to carry its own fire, the imagination opens further. If sunlight can push a sail, then perhaps a powerful beam can push harder. If a tether can transfer momentum from infrastructure to vehicle, perhaps other systems can push ships from afar without onboard propellant. The next step takes this idea and stretches it toward the edge of deep space, where lasers, particle beams, and distant power stations might one day send tiny craft racing across distances that chemical rockets could never manage alone. Once we begin imagining spacecraft that do not carry all their own push, the whole idea of travel starts to change. A rocket is a very self-contained machine. It brings its engine, its fuel, its tanks, its pumps, its fire, and its burden all together. It is a traveller carrying not only a suitcase, but also the road, the horse, the hay for the horse, and a small barn in case the horse gets tired. That approach works when the journey is short enough and the first obstacle is severe enough. Earth is severe. Earth requires force. But between worlds, where the great distances open up and the silence stretches for millions of kilometers, we can ask a different question. What if the engine did not have to be fully on the spacecraft at all? This is the dream behind beamed propulsion. Instead of carrying all the energy needed for motion, a spacecraft could receive energy from far away. A powerful laser, or perhaps a beam of charged particles such as electrons, could push on a sail or interact with a magnetic field around the spacecraft. The pushing system might stay near Earth, near the Moon, in orbit around the Sun, or at some future deep space station. The spacecraft itself could be much lighter because it would not carry the same vast store of fuel or the same heavy engine. It would be more like a sailboat using wind, except the wind would be built by engineers, aimed across space, and turned on with enough precision to make everyone in the control room sit very still. At first, this sounds almost like cheating. If a spacecraft does not bring the engine with it, have we really made a spacecraft, or just a very expensive kite? But transportation has always used outside systems. A train does not carry the track. An electric tram may draw power from lines above it. A sailing ship uses wind it did not make. A car depends on roads, fuel stations, signs, and bridges. We do not think of those vehicles as incomplete because they use infrastructure. We think of them as part of a network. Beamed propulsion asks whether space travel can also become a network, with power sources and pushing systems separated from the craft they move. Lasers are the easiest version to picture, even if the engineering is anything but easy. A laser produces light that is highly organized, directed, and concentrated. If you shine an ordinary lamp into the night, the light spreads everywhere, like gossip at a family gathering. A laser, by contrast, can form a narrow beam. Over space distances, even laser beams spread, but they begin with a kind of order that makes long-distance pushing imaginable. If such a beam is aimed at a reflective sail, the light can transfer momentum to the sail. The push is small compared with a rocket engine, but if the beam is powerful enough, the sail light enough, and the aiming precise enough, that push could become significant. This is where the idea becomes especially interesting for very small spacecraft. A large crewed ship is heavy. It needs shielding, life support, structure, power, communications, and perhaps a place for someone to float quietly while regretting their snack choices. Pushing such a vehicle with a beam would require enormous power and enormous sail systems. But a tiny robotic probe could be different. If the spacecraft is extremely light, perhaps only carrying a small camera, sensors, a communication system, and a thin sail, a powerful laser could accelerate it to speeds far beyond what chemical rockets could manage. It might cross distances that would otherwise take thousands of years in a much shorter time. This is why beamed propulsion often appears in conversations about interstellar travel. The nearest stars are so far away that ordinary rockets become painfully slow. Even nuclear propulsion, at least in the near-term forms we understand best, may not be enough to send large craft across interstellar space within a human lifetime. But a very light sail pushed by a very powerful beam changes the balance. The spacecraft does not have to carry its own fuel for acceleration. The heavy machinery stays behind. The probe is pushed from afar, then coasts into the dark at tremendous speed. It would not be a starship like the ones in films, with corridors, windows, and a calm captain drinking tea. It would be more like a tiny message thrown hard enough to cross the night. There is something both thrilling and slightly lonely about that image. A small craft, perhaps no larger than a hand in some concepts, racing away from the solar system after a brief but intense push from light. Once the beam stops, it continues on its path, silent and fast. It cannot easily slow down when it reaches another star, at least not with the simplest version of the idea. It may fly past its target quickly, gathering data in a short encounter and sending faint signals back across years of distance. That may sound modest, but it would still be extraordinary. The first close images from another star system would be a new kind of human vision. Not footsteps, not flags, not cities, but a few pieces of knowledge carried home by light. The challenges are enormous. First, the laser system would need to be extremely powerful, not just a laboratory pointer, not the kind used in presentations by someone who keeps circling the wrong part of the slide, but a large coordinated array capable of delivering vast energy into a beam. Building such a system would require power generation, cooling, optics, control, safety systems, and political confidence. A laser powerful enough to push spacecraft across interstellar distances is not a casual household appliance. it would be infrastructure on a planetary or space-based scale. Second, the beam must stay focused over huge distances. Light spreads, even when it begins as a laser. The farther the sail is from the source, the harder it is to keep enough light on it. This means the beam system may need a very large aperture, careful phasing between many smaller lasers, and constant correction for disturbances. If the laser is based on Earth, the atmosphere becomes another problem. Air bends, scatters, and distorts light. Astronomers already deal with this when trying to look out at the universe. Beamed propulsion would need to send a powerful beam out with exquisite precision, which makes space-based laser arrays attractive in some long-term visions. Of course, putting giant laser infrastructure in space is not exactly a weekend project. Third, the sail itself must survive the beam. A laser can push, but it can also heat. If the sail absorbs too much energy, it may warp, melt, tear, or turn into a brief and expensive sparkle. The sail must be extremely reflective, extremely light, and able to handle intense illumination. It must keep its shape while being accelerated. It must not tumble in a way that loses the beam. It must not wrinkle like a piece of foil being handled by a nervous giant. Material science becomes as important as propulsion. The whole dream may depend on making sails so thin and strong that they feel almost unreasonable, which is often how future technology feels before it becomes ordinary. Fourth, the aiming is unforgiving. If you are pushing a small sail across space, a tiny pointing error can become a huge miss over distance. The beam must track the sail accurately, while the sail is moving faster and farther away. Communication delays grow. The craft becomes faint. The beam must be controlled with extraordinary accuracy. It is a little like trying to push a falling leaf with a flashlight from another continent, except the leaf is racing away from you at extreme speed, and the flashlight has the seriousness of a national energy system. And then there is the problem of slowing down. A laser beam from home can push a craft away from home, but once the craft reaches another star, how does it stop? For a flyby probe, it may not need to stop. It can race past and collect data. But for orbiting another star or landing on a planet, slowing down is essential. Some concepts imagine using the light or solar wind of the destination star to brake. Others imagine magnetic sails interacting with interstellar particles. Some rely on complicated mission designs. None are easy. Acceleration is only half the journey. Arrival is the other half, and arrival has a habit of making bold ideas suddenly more humble. Electron beams and other particle beams bring a related but different set of possibilities. Instead of pushing with light, a particle beam sends streams of charged particles across space. Electrons are charged, and charged particles can interact with magnetic fields. A spacecraft might carry a magnetic sail, a large magnetic field extending around it like an invisible net. A beam of particles could transfer momentum to that magnetic field, pushing the craft without needing a solid sail in the ordinary sense. This could allow a vehicle to be pushed from afar while avoiding some of the limits of fragile reflective sails. At least, that is the hope. Particle beam propulsion has its own difficulties. Charged particles repel each other, so a beam of electrons does not naturally want to stay neatly bundled. It tends to spread. Magnetic and electric effects become complicated. Space is not perfectly empty either. It contains particles, fields, and plasma that can disturb a beam. Keeping a particle beam focused over long distances may be extremely difficult. One idea is to use a neutralized beam, mixing positive and negative charges so the beam does not blow itself apart as easily. Another is to use clever magnetic structures or stage systems, but the engineering quickly becomes demanding. A beam that looks tidy in a diagram may behave like a very energetic flock of birds once released into space. Still, particle beams are attractive because they can, in principle, transfer momentum without the spacecraft carrying the whole engine. They might push magnetic sails, help accelerate cargo, or support deep space transportation networks. They may also offer ways to deliver energy to spacecraft that then use it for onboard propulsion. The details vary, but the theme remains the same: Move the heavy power source away from the vehicle. Let the spacecraft be lighter. Let infrastructure do some of the work. This is the opposite of the old lone rocket, rising with everything it owns and spending itself as it climbs. Beamed propulsion also raises a practical question about where such systems should be built. Earth has industry, power grids, people, and maintenance. But Earth also has atmosphere, weather, rotation, politics, and the small inconvenience that anything very powerful pointed upward tends to make people ask questions. The Moon offers no atmosphere, stable ground, and long views of space, but it lacks the infrastructure we take for granted. Orbit offers freedom from weather and atmosphere, but building and maintaining large systems in orbit is hard. A solar orbiting platform could have constant sunlight and a clear line of sight for certain missions, but would be far from easy to assemble. Every location solves one problem and creates another. Space engineering is very fair in that unpleasant way. There are safety issues too. A powerful beam intended to push spacecraft is still a powerful beam. It must be aimed responsibly. It must not threaten satellites, aircraft, habitats, or unintended targets. If the system is in space, it must be controlled securely. The same ability to deliver concentrated energy over long distances that makes beamed propulsion useful also makes it politically sensitive. A future with giant propulsion lasers would require agreements, transparency, safeguards, and probably a large number of meetings where everyone tries to sound calm while discussing a machine that can shove objects across the solar system with light. This may sound like a reason to dismiss the idea, but many transformative technologies begin as infrastructure problems wrapped in anxiety. Railways required land, laws, steel, bridges, signals, stations, and public trust. Aviation required airports, traffic control, safety standards, and international agreements. Space-based beamed propulsion would require an even greater version of that maturity. The technology is not just the beam. It is the civilization capable of building, governing, and using the beam safely. The most exciting part is that beamed propulsion could separate launch from acceleration in a new way. A spacecraft might be launched gently into orbit by conventional means, assembled or deployed there, and then accelerated by a distant power system. For cargo in the solar system, beams could assist transfers without each vehicle carrying large propellant reserves. For tiny interstellar probes, beams could provide the tremendous initial push needed to make the journey meaningful on human timescales. These are different missions, different scales, and different levels of difficulty, but they all point toward the same future. Space travel is a relationship between vehicles and infrastructure, rather than a single machine burning alone. There is a lovely historical echo here. Early humans did not cross oceans by carrying wind in barrels. They built sails. Later, they did not move trains by putting every piece of track inside the locomotive. They built railways. They did not make air travel common with one heroic airplane. They built airports, refueling systems, navigation networks, maintenance crews, weather services, and rules of the sky. The vehicle matters, but the network makes travel repeatable. Beamed propulsion suggests that deep space may one day need its own network. Power stations, beam arrays, receiving sails, magnetic sails, guidance systems, orbital assembly yards, and routes planned not only by where planets are, but by where the infrastructure can push. For now, much of this remains experimental or conceptual. We're not sending large starships on beams tomorrow. We're still learning how to make sails light enough, beams precise enough, systems safe enough, and missions practical enough. But the idea matters because it breaks the emotional habit of thinking every spacecraft must carry all its own strength. It asks us to imagine propulsion not as something trapped inside a vehicle, but as something that can be shared across distance. A beam can reach out, a sail can receive, a craft can move because energy was sent to it, not stored within it from the beginning. In a way, this makes space travel feel less like throwing a stone and more like playing music across emptiness. The beam is the instrument, the sail is the string. The spacecraft moves when the two are tuned together, That may sound gentle, but the engineering would be severe. A tiny error, a weak material, a distorted beam, a power failure, or a missed alignment could decide the fate of a mission. Beam propulsion is delicate and powerful at the same time, which is a difficult combination. Like balancing a teacup on a rocket engine, only with more mathematics and fewer biscuits. The dream of pushing ships from afar also forces us to think about what kind of explorers we want to send. Humans want to go places. We want boots on dusty ground, hands on instruments, eyes looking through windows. But the first interstellar explorers may not be humans at all. They may be tiny machines, light enough to be accelerated by beams, simple enough to survive, and patient enough to cross the dark without complaint. This does not make the dream smaller, it may make it possible. Before people crossed oceans, scouts and stories moved ahead. Before human beings walked on the moon, robotic spacecraft mapped and tested the way. Before any future starship carries life between stars, a small beamed probe may go first, carrying our curiosity in miniature. And what would it mean if such a probe succeeded? Imagine receiving a signal from a spacecraft that had passed close to another star. Not an image from a telescope near Earth, but data from something we built, something that crossed interstellar space and looked back at a new sun from nearby. The signal would be faint. It would take years to arrive. The images might be few. The science might be limited by the speed of the flyby. And yet, it would be one of the most profound messages in human history. It would mean that we had extended touch, however lightly, beyond the solar system. Not with a rocket carrying all its fuel, but with a beam of energy and a small sail sent into the dark. Still, there is a long distance between possible and practical. Beamed propulsion must solve power, pointing, materials, control, communication, braking, safety, cost, and governance. That is quite a list. Long enough, perhaps, to make an engineer stare quietly into a mug for several minutes. But hard lists do not mean impossible lists. They simply tell us where the work lives. Rockets were once impossible. Controlled flight was once impossible. Landing on the moon was once absurd to many sensible people. The future often begins as a collection of problems that look unreasonable when placed neatly in a row. What makes lasers and particle beams important in this story is not that they are guaranteed to replace rockets. They are not. Rockets will remain essential for many tasks. What matters is that they show how far our thinking has moved. We're no longer only asking how to carry more fuel. We're asking how to carry less. How to move energy without moving tanks. How to use light, charged particles, and magnetic fields as part of a transportation system. How to push without touching. How to turn distance itself into something a machine can cross by receiving help from home. Beyond this point, the ideas become even stranger. Once we start talking about sending energy across space, pushing sails with lasers, catching particle beams with magnetic fields, and racing tiny probes toward other stars, we are already standing near the border between practical engineering and speculative physics. And just beyond that border waits the most famous dream of all, the dream not merely of moving through space faster, but of changing the shape of space around the journey itself. By the time we reach ideas like warp drives and starships, we have already travelled a long way from the launch pad. We began with fire, fuel, thrust, and the hard climb away from Earth. Then we moved into quieter methods, electric engines that push for years, nuclear propulsion that may shorten the road to Mars, solar sails that catch sunlight, tethers that trade motion, and beams that might one day push small craft from afar. Each idea tries to loosen one part of the old rocket problem, carry less fuel, use energy more wisely, let space itself help. But the stars remain stubbornly far away. Even after all that cleverness, the distance between star systems is so large that it makes the solar system look almost cozy, like a small neighbourhood with unusually distant streetlights. This is where the imagination starts to become restless. Mars is hard, but Mars still belongs to our solar system. The outer planets are far, but they still orbit the same sun. The nearest stars are different. They are not just far in the ordinary sense. They are far in a way that almost breaks our daily understanding of distance. If you drove a car non-stop around Earth, you could eventually understand the scale of the planet. If you flew around the world, you could shrink it into hours. But the nearest stars are so distant that even light, the fastest thing in the universe, takes years to cross the gap. Our spacecraft, moving far slower than light, would need thousands or tens of thousands of years with today's technology. That is not a journey in the usual sense. That is a message in a bottle thrown into an ocean, where the shore is older than civilization. So naturally humans ask the forbidden-sounding question: is there a way around the limit? Not through it, perhaps, but around it. If nothing can travel faster than light through space, could space itself somehow be used differently? Could a ship ride a distortion of space rather than simply moving through it? Could the distance ahead be shortened, the distance behind expanded, and the craft carried along inside a pocket where local rules are not broken? This is the basic dream behind the warp drive, one of the most famous speculative ideas in modern physics. It sounds like science fiction because it is beloved by science fiction, but it also has a real, if highly uncertain, place in theoretical discussions about general relativity. General relativity, Einstein's theory of gravity, changed the meaning of space and time. Space is not just an empty stage where objects move. It can curve, it can stretch, it can be shaped by mass and energy. Around planets, stars, and black holes, space and time are warped, and objects follow paths through that curved geometry. This is not a metaphor in the simple decorative sense. It is how gravity works in the theory. Earth orbits the sun not because an invisible hand pulls it in the old classical way, but because the sun shapes space-time, and Earth follows a path through that shape. If space-time can bend naturally, the question becomes whether an advanced civilization could make it bend artificially. The warp drive idea asks whether a bubble of space-time could be created around a spacecraft. Inside the bubble, the ship might remain locally at rest, not breaking the rule that nothing moves faster than light through its immediate region of space. But the bubble itself would alter the space around it, shrinking space in front and expanding space behind. In a loose way, the destination becomes closer because the geometry between here and there has been manipulated. The ship does not outrun light in the normal sense. Instead, the road changes beneath it. If that sounds slippery, it is because it is. The idea lives at the edge of what our equations can describe, not at the level of something engineers can build. The first thing to say clearly is that warp drives are not available technology. They are not hidden in a laboratory. They are not waiting for a few better batteries and a brave pilot. They are speculative solutions inside a theory that allow certain shapes of space-time under very unusual conditions. Those conditions may require forms of energy or matter that we do not know how to create in the needed amounts, and perhaps cannot create at all. In many versions of the idea, the warp bubble needs negative energy or exotic matter. This is not simply ordinary antimatter or a strange fuel you could order if the space agency had a better budget. Negative energy is a deeply subtle concept, appearing in limited ways in quantum physics, but not as something we can pile into tanks like rocket propellant. This is where the dream meets the wall. General relativity allows strange geometries on paper, but allowing something in an equation is not the same as making it physically possible. A map can include a bridge, but the bridge still needs steel, foundations, money, maintenance, and someone to explain why it does not immediately fall into the river. The warp drive is a little like that, except the bridge is made of space-time and may require energy conditions the universe does not usually permit. The question is not only how to build it, the question is whether nature allows it in the first place. Even if exotic energy were possible, other problems appear. A warp bubble would need to be controlled. It would need to form around a craft, move, steer, and stop. Stopping is not a small detail. In ordinary travel, slowing down is always part of the journey. With a warp bubble, the question of how to arrive safely becomes deeply complicated. What happens to particles and radiation collected along the way? What happens at the front edge of the bubble? What happens to the region of space near the destination when the bubble collapses or slows? Some analyses suggest serious hazards, including intense radiation effects. Others depend on different assumptions and designs. The point is not that we have a complete answer. The point is that turning a mathematical possibility into a safe vehicle is an enormous leap. There is also a communication problem. If parts of the warp bubble behave in ways that place them beyond normal light speed contact with the ship inside, then controlling the bubble from within may be impossible in certain designs. Imagine building a car where the steering wheel cannot send instructions to the front wheels while the car is moving. That would be inconvenient, especially during turns. Some warp concepts face similar issues, though in far more technical form. The vehicle might not be able to create, control, or dismiss its own bubble in a straightforward way. This is one of those details science fiction can solve with a glowing console, but physics tends to ask follow-up questions. Yet, the idea continues to attract attention because it touches the deepest wish of interstellar travel. Rockets, ion engines, nuclear propulsion, sails and beams all still move through space in the usual sense. They can be faster, more efficient, or more clever, but they still face the enormous distance directly. A warp drive is different because it tries to make distance itself part of the machinery. It asks whether the geometry of the universe can be engineered. That is an extraordinary thought, perhaps too extraordinary. But it shows how far the human imagination will go when distance refuses to cooperate. Wormholes live nearby in this same region of speculative physics. A wormhole is often imagined as a tunnel connecting two distant points in space-time. Instead of crossing the space between stars, one might pass through a shortcut. Again, general relativity allows certain wormhole-like solutions, but keeping a wormhole open may also require exotic matter or negative energy. Natural wormholes, if they exist at all, may be microscopic, unstable, or impossible to use. A traversable wormhole large enough for a ship is not something we know how to build. It is not even something we know can exist in a stable, useful form. But like warp drives, wormholes force us to examine what space-time might permit at its most extreme. It is tempting to dismiss all of this as fantasy, and perhaps some of it will turn out to be just that. But there is value in studying the edge. The boundary between possible and impossible is not always obvious until we press on it. Scientists do not only study technologies ready for next year's launch schedule, they also study the rules, limits, and strange corners of theories. Sometimes those studies confirm that a dream is impossible. That is useful. Sometimes they reveal a smaller, more realistic version of the dream. That is useful too. And sometimes they simply deepen our understanding of the universe, even if no machine ever comes from it. Not every road leads to an engine. Some roads lead to knowledge, which is less dramatic on a poster, but often more important. Starships, even without warp drives, present their own extraordinary challenges. A true starship would need to survive for years, decades, or longer. It would need power, navigation, shielding, communication, autonomy, and a way to protect itself from tiny particles in interstellar space. At very high speeds, even a grain of dust can become dangerous. Space is emptier than any vacuum we can easily make on Earth, but it is not perfectly empty. A starship crossing the gap between stars would meet atoms, dust, cosmic rays, magnetic fields, and unknown hazards over enormous distances. The faster it travels, the more serious those impacts become. Speed is desirable, but speed makes the environment harsher. For robotic starships, these problems are difficult but at least simpler than for human crews. A machine can be small, it can sleep through long stretches, it can tolerate cold, darkness, and silence. It does not need a kitchen, a medical bay, exercise equipment, or a calm person reminding everyone that the mission is going very well despite the mysterious blinking light. A human starship is another matter. It would need to become a travelling habitat. It would need to support life not for days or months, but perhaps for generations, unless the propulsion system were extremely fast. The ship would need closed ecological systems, social stability, repair capacity, manufacturing, medicine, governance, education, and all the ordinary human complications that occur when people live together for a very long time in a place with no outside. Generation ships are one possible answer. Instead of reaching another star within one lifetime, a large vessel would travel slowly enough that many generations are born, live, and die during the journey. The descendants arrive at the destination, not the original crew. It is a powerful idea, and also a deeply unsettling one. The first travellers would choose the mission, but later generations would inherit it. They would live inside a project they did not personally begin, moving toward a world they have never seen, based on the hopes of ancestors. That raises scientific, ethical, social and emotional questions. A generation ship is not just a vehicle. It is a civilization in a container, and civilization is not known for being a simple payload. Another idea is suspended animation, or some future form of long-term biological preservation. People sometimes imagine crews sleeping through the journey and waking near another star. This appears often in fiction, partly because it solves the storytelling problem of waiting centuries between scenes. But real biology is not so easy. Human bodies are not designed to be paused like music. Lowering metabolism, preventing damage, maintaining tissues, protecting the brain, and reviving a person safely after long periods would require breakthroughs far beyond current medicine. Some animals can hibernate or survive extreme states, but copying those abilities in humans is a major challenge. Perhaps future biology will change what is possible. For now, sleeping across the stars belongs more to speculation than mission planning. A faster starship might avoid the generation problem, but then propulsion becomes the central difficulty again. Fusion engines, antimatter concepts, and beamed sails all appear in serious and semi-serious discussions because chemical rockets cannot come close. Fusion might provide far greater energy than chemical reactions, but controlled fusion propulsion is far beyond our present spacecraft capabilities. Antimatter would be even more energy dense, but producing it, storing it, and using it safely are enormous problems. Antimatter is not a fuel we can casually manufacture by the barrel. It is extremely difficult to produce in meaningful amounts, and would need to be confined with exquisite care, because if it touches normal matter, it annihilates. Useful, perhaps, but not the sort of thing you want rattling around loosely in the cargo hold. Interstellar travel also turns communication into a slow conversation. Even if a probe reaches another star, its signals take years to return. A human mission would be isolated in a way no explorer on Earth has ever been. There would be no quick call home, no real-time support from mission control, no immediate rescue. The ship would need to be self-reliant. Every important system would need redundancy, repairability, and resilience. A starship is not simply a faster spacecraft. It is an independent world with engines. This is why the word starship can be misleading. It sounds like one object, one grand machine, one dramatic silhouette against the stars. But a real starship would be a combination of many mature technologies: propulsion, power, materials, radiation shielding, artificial gravity perhaps, life support, closed-loop recycling, autonomous navigation, robotics, medicine, psychology, communication, manufacturing, agriculture, if humans are aboard. It would not be built by propulsion alone. A warp drive without life support is not a starship. A powerful engine without shielding is not a starship. A beautiful hull without repair systems is not a starship. The romance of the starship rests on a mountain of quiet, practical details, and still, The dream persists. Perhaps it persists because the stars are not just places. They are symbols of distance, mystery, and possibility. Humans have always looked at horizons and wondered what lies beyond them. The far hill, the far ocean, the far continent, the far moon. Each time we reached one boundary, the next one appeared. The stars are the largest version of that old pattern. They ask whether intelligence can become patient enough, careful enough, and wise enough to cross distances that were not designed for us. There is a risk in talking about warp drives and starships too casually. It can make real space exploration seem disappointing by comparison. Mars can seem small if we spend too much time dreaming of distant stars. The moon can seem ordinary if we imagine bending space-time, but the opposite should be true. The harder interstellar travel looks, the more impressive our near-term steps become. Building a sustainable presence near Earth, returning to the moon, learning to use lunar resources, sending humans to Mars, developing nuclear propulsion, mastering electric cargo transport, testing sails and tethers, building space infrastructure, all of these are not distractions from the stars. They are the first lessons. You do not build a starship by skipping the solar system. You build a starship by learning how to live and work in space one difficult skill at a time. Maybe warp drives will remain impossible. Maybe wormholes will stay as mathematical ghosts. Maybe the first true interstellar craft will be a tiny laser-push sail rather than a crude vessel. Maybe the dream of human starships will take centuries or longer, or change into something we cannot yet picture. That uncertainty is not a failure. It is the honest shape of the frontier. The edge of possible physics is not a clean line. It is a foggy coastline. Some things that look solid may vanish as we approach. Some things that look impossible may reveal narrow paths. The work is to keep looking without pretending we have already arrived. For now, rockets are still our beginning. Ion engines are still our patient tools. Nuclear propulsion is still a serious candidate for faster planetary travel. Sails, tethers, and beams are still developing ideas with different levels of promise. Warp drives and starships sit farther out, where physics becomes speculative and engineering becomes almost dreamlike. But they matter because they remind us that the future of space travel is not only about improving engines, it is about asking what motion means when the distances become vast. It is about learning whether the universe allows shortcuts or whether it demands patience. It is about discovering whether we can make machines that do not simply burn harder, but think more deeply with the structure of space itself. And as strange as these ideas are, they return us to a very familiar human habit. We look at a limit, and at first we accept it, then we measure it, then we argue with it, then we build tools around it. The sky was once a limit, the ocean was once a limit, the atmosphere was once a limit, Earth's gravity was once a limit. Each one remained real, but none remained absolute in the same way. The stars may be the next great limit, and perhaps they will demand technologies we do not yet know how to make or even how to name. Before we can reach them, though, we need to gather the whole story together, from chemical rockets to speculative starships, and ask what the next great leap into deep space might actually look like. When we step back from all these ideas, from chemical rockets to ion engines, from nuclear propulsion to solar sails, from space tethers to laser-pushed probes and the distant dream of warp drives, a clearer picture begins to form. The future of space travel will probably not belong to one single engine. It will not be one heroic machine that solves every problem, lifts from every planet, crosses every distance, lands on every world and returns home in time for tea. That would be convenient, certainly. It would also be very unlike the way real transportation develops. The future usually arrives as a collection of tools, each one good at a different task, each one filling a gap left by the others. Chemical rockets gave us the first real step. They are the reason we're even having this conversation. Without them, the dream of deep space would still be trapped on the ground, staring up through the atmosphere. Rockets broke the seal between Earth and sky. They carried satellites, astronauts, telescopes, probes, landers, rovers, and all the early machinery of the space age. They showed us that our planet was not a prison, even if it does hold on rather firmly. they also taught us something humbling. Getting into space is not the same as being able to travel freely through it. Reaching orbit is a beginning. The deep road is much longer. That is the central lesson of this whole journey. Rockets are not the enemy of the future. They are the doorway to it. But a doorway is not a highway. A launch is not an interplanetary transport system. A tower of fuel can lift us above the weather, but once we are in space, the scale of the problem changes. The question is no longer only how do we escape Earth. The question becomes how do we move through a solar system that is larger, colder, slower, and more demanding than our old launch imagery prepared us to imagine. To answer that, we need more than fire. We need strategy. A mature space future may begin with something simple to say and hard to build. Use the right engine for the right part of the journey. Chemical rockets may lift people and cargo from Earth. Reusable boosters may lower the cost of reaching orbit. Spacecraft may assemble or refuel above the atmosphere. Nuclear propulsion may send crews toward Mars on faster paths. Electric thrusters may move cargo slowly and efficiently between useful orbits. Solar sails may carry lightweight probes without burning propellant. Tethers may help transfer momentum and reduce fuel needs along repeated routes. Laser beams may push tiny craft toward nearby stars. Each method does not replace the others. Each one takes over where another becomes weak. This is how transportation works on Earth too. We do not use the same vehicle for everything. We do not cross an ocean on a bicycle, except perhaps in a very strange dream. We do not fly across continents in a canoe. We use cars, trains, ships, aircraft, elevators, cables, roads, ports, and fuel networks. The world became connected not because one vehicle became perfect, but because many systems learned to cooperate. Space may need the same kind of cooperation. The first true age of deep space travel may look less like one giant rocket and more like a network of launch vehicles, orbital stations, fuel depots, cargo tugs, transfer vehicles, landers, habitats, and power systems. That may sound less glamorous than a single shining starship, but it's probably more realistic. Infrastructure is often quieter than adventure, but it is what makes adventure repeatable. A launch pad is infrastructure. A tracking network is infrastructure. A space station is infrastructure. A refueling depot would be infrastructure. A lunar base that makes oxygen or propellant would be infrastructure. A Mars cargo system would be infrastructure. A giant laser array, if it ever exists, would be infrastructure. The future of space may depend on less dramatic things than engines alone. Tanks, docking ports, storage systems, solar arrays, radiators, communications relays, repair robots, standard connectors, excellent valves. Space exploration, when seen up close, often turns out to be romance supported by very serious plumbing. The moon may become part of that next step, not because it is the final goal, but because it is close enough to practice. It has low gravity compared with Earth, no thick atmosphere, and resources that may be useful if we learn how to extract and process them. Ice in shadowed regions could become water, oxygen, or propellant. Lunar materials could one day support construction. A base there could help test life support, surface operations, power systems, dust control, and the psychological reality of living away from Earth. The moon is not easy. It is airless, dusty, harsh, and cold in ways that make ordinary machinery reconsider its career choices. But it is nearby by space standards, and nearby matters when you are learning. Mars is the more demanding test. It is far enough that crews cannot rely on quick rescue. It has a thin atmosphere, lower gravity than Earth, dust storms, cold conditions, and radiation concerns. It also has a surface, a day length not too different from Earth's, water ice, carbon dioxide in the air, and landscapes that invite study. Going to Mars is not only a propulsion problem, it is a complete systems problem. We need better engines, yes, but also better habitats, better radiation protection, better medical planning, better food systems, better recycling, better landing systems, better surface power, and better ways to use what is already there. A faster engine helps, but it does not wash the dishes, grow the lettuce, seal the habitat, or keep dust out of the machinery. That is why the next great leap into deep space will probably be practical before it is spectacular. It may not begin with humans standing on another world in a dramatic sunrise. It may begin with cargo sent ahead, a habitat delivered years before the crew arrives, a power station tested on the surface, a small factory making oxygen from local materials, a fuel depot operating in orbit, a tug slowly moving supplies using electric propulsion, a nuclear stage tested far from Earth, a solar sail demonstrating a new kind of maneuver, a tether proving it can transfer momentum safely. These steps may not fill movie trailers with thunder, but they are the bricks from which a real spacefaring future would be built. There is a useful difference between exploration and transportation. Exploration can happen once. Transportation must happen again and again. A single heroic mission can accept unusual risk and cost. A transportation system cannot. If humans are to travel regularly beyond Earth, the goal is not simply to make one mission succeed. The goal is to make the next mission easier because the first one happened. Each flight should leave behind knowledge, equipment, infrastructure, or confidence. Each mission should reduce the difficulty of the next. That is how a frontier becomes a route. Not quickly, not smoothly, but through repetition, maintenance, learning, and the patient removal of surprises. Rockets alone do not give us that future because rockets make each journey carry too much of its own beginning. They are powerful, but they reset much of the challenge every time. Launch, burn, discard, coast, arrive if all goes well. The deeper future asks for systems that stay. A depot stays, a station stays, a tether stays, a cargo route stays, a lunar processing plant stays, a power system stays. These things allow each new mission to build on the last. That is the difference between visiting space and beginning to live with space as an environment. Living with space also means accepting its limits. Deep space is not a place that rewards carelessness. It is not an empty version of Earth where the main problem is distance. It is radiation, vacuum, temperature extremes, communication delays, isolation, dust, micrometeoroids, gravity changes, and the constant need for systems to work without easy repair. Better propulsion can reduce some risks, especially travel time, but it cannot remove the need for discipline. The next great leap will require patience as much as boldness. It will require long testing, repeated missions, careful failures, and honest lessons. Space does not mind enthusiasm, but it prefers preparation. Still, the direction is exciting. Imagine a future Mars mission assembled in orbit from pieces launched on reusable rockets. Cargo has already gone ahead using efficient electric propulsion. A nuclear transfer stage waits, checked and fueled. Supplies are already in Mars orbit or on the surface. A lander has been tested. A habitat is producing oxygen before the crew even leaves Earth. The crew departs not in a desperate one-shot mission, but as part of a prepared route. The trip is still dangerous, still difficult, still worthy of respect, but it is no longer only a stunt. It is a system working as designed. That is what progress may look like. Not removing danger completely, but replacing improvisation with preparation. Now imagine the outer solar system. Robotic craft powered by nuclear electric systems move through the dark where sunlight is weak. They visit icy moons, orbit distant planets, and perhaps explore subsurface oceans where life might exist. Cargo moves slowly but efficiently. Small probes use sails or advanced electric propulsion to study the sun, asteroids, comets, and the space between planets. Human crews may not go everywhere at first. They do not need to. Machines can go ahead, build maps, test resources, and answer questions. Humans follow where the case is strongest, where the systems are ready, and where the purpose is clear. Exploration becomes a layered process. not one leap into the unknown with crossed fingers and a heroic playlist. And then, perhaps much later, the first interstellar attempt. Not a giant crude starship at first, most likely. More likely a tiny probe, pushed by a beam or carried by some future propulsion system we're only beginning to imagine. It may be small enough to seem almost disappointing compared with fiction. No corridors, no sleeping crew, no windows looking out on the galaxy, but it could still be the first object built by humans to pass close to another star. It could send back a few measurements, a few images, a faint signal moving at the speed of light through years of darkness. That would not be the end of rockets. It would be the proof that rockets were only the opening sentence. It is important to keep our expectations honest. There is no guarantee that warp drives will become real. No guarantee that fusion starships will be practical. No guarantee that giant laser arrays will be built. No guarantee that human beings will walk on Mars soon, or settle the moon easily, or turn asteroids into fuel stations on a neat schedule. The future is not a promise written in the stars. It is a set of possibilities that require work, money, cooperation, time, and more than a little humility. But uncertainty is not the same as emptiness. We know enough to see directions. We know chemical rockets have limits. We know electric propulsion works in useful ways. We know nuclear energy offers higher performance if handled responsibly. We know light can push. We know orbital mechanics can be used cleverly. We know the fuel problem is real, and we know many ways to begin reducing its grip. The story of space travel is therefore not a story of abandoning rockets in disappointment. It is a story of outgrowing the idea that rockets must do everything. A child may first learn to walk by holding a hand, then later runs, rides, drives, flies, and perhaps one day travels in ways the child could never have named. Rockets are our first strong handhold. They pulled us upward. They showed us Earth from outside. They carried the first footprints to the moon. They deserve their place in history, and they will have their place in the future too. But if humanity is going farther, much farther, then rockets must become part of a larger family. There is a comforting pattern here. Every great limit feels final until it becomes a field of study. The ocean was once a barrier, then it became a route. The sky was once unreachable, then it became crowded with wings. Space was once beyond all machines. Then a small satellite crossed the night, and people looked up knowing something made by human hands was moving above them. The moon was once a distant lamp in the sky. Then it held footprints. Each limit did not vanish. The ocean remained dangerous. The sky remained unforgiving. Space remained difficult. But knowledge changed our relationship with the limit. We learned how to enter it, how to survive it, how to move through it with better tools. Deep space is the next version of that lesson. The distances are larger than anything we have faced before. The energy demands are severe. The timescales are uncomfortable. The technology is incomplete. But the path is not blank. It begins with the same practical questions repeated in new forms. How do we carry less? How do we use more of what is already there? How do we build systems that last? How do we protect people? How do we send machines ahead? How do we make one journey help the next? How do we turn a heroic launch into a dependable route? Maybe the first deep space highways will not look like highways at all. They may be sequences of orbits, depots, transfer windows, solar electric cargo lanes, nuclear crew vehicles, lunar supply chains, and laser paths for tiny probes. The map may be invisible to the eye, made not of roads, but of timing, gravity, energy, and infrastructure. A ship may not simply depart from Earth and go. It may climb to orbit, dock, refuel, wait, transfer, coast, receive a push, adjust with electric thrust, brake with an atmosphere, land with chemical engines, and then use local resources to prepare for the next leg. Future space travel may be less like firing an arrow and more like moving through a carefully built system of handoffs. That may be the real sign that rockets are no longer the whole future, not when they disappear, but when they stop being alone, when launch becomes only the first service in a chain, when fuel is stored in orbit, when cargo moves without hurry, when crews take faster vehicles because the slow supplies are already waiting, when spacecraft use sunlight, magnetism, gravity, nuclear heat, electric fields, and beams from home. When the question is not, can we launch this entire mission at once, but what part of the space transportation network will carry it next? For now, we're still near the beginning. We're still learning how to reuse rockets well, how to live in orbit for long periods, how to return to the moon, how to prepare for Mars, how to power spacecraft far from the sun, how to make small engines push for years, how to unfurl sails, how to test new materials, and how to keep people safe in places that were never built for us. That beginning is not small. It is one of the largest projects our species has ever attempted. And like all large projects, it advances through details: a better engine test, a lighter tank, a safer reactor design, a more reliable docking system, a cleaner life support loop, a more accurate navigation method. Progress is often less dramatic than the dream, but it is the only road the dream can stand on. And so, dear listener, as we settle near the end of this quiet journey, perhaps the most honest answer is this: rockets are not the future of space travel because they are only the beginning of space travel. They are the fire at the doorway, the first fierce shove, the tool that lets us leave the ground. Beyond them lies a much wider story: engines that whisper for years, reactors that may shorten the road to Mars, sails that catch sunlight, tethers that trade motion, beams that push from afar, speculative drives that ask whether space itself has deeper secrets. Some of these ideas will succeed, some will fail, some will change shape as we learn more, but all of them come from the same human refusal to stop at the first answer. If you found this journey soothing, or if it gave you a little more wonder for the quiet machinery of the future, I would be ever so grateful if you gave the video a like and maybe subscribed. It helps this calm little corner of science reach others who might enjoy drifting through big questions at a gentle pace. And before you go, I would still love to know where you are listening from tonight. Are you under city lights, country stars, a cloudy sky, or a window reflecting your own room back at you? Somewhere above all of us, rockets are still rising, satellites are still circling, probes are still coasting, and the future is still being assembled one careful piece at a time. Sleep well, fellow traveller. The stars are far, and rockets alone may not carry us all the way. But every journey begins with the first machine that proves the ground is not the end. And somewhere beyond the flame, beyond the fuel, beyond the old limits of distance and time, the next way forward is waiting for us to build it.